Okay. Um, Good morning, afternoon, or evening, everyone. I am Milton Aguirre. Welcome to the final day of the ISAAC-ICMAM Conference of Women in Mathematics 2024. I hope you are all doing well, that you enjoyed the previous 2 days of the event. It is my great pleasure to introduce Dr. Rajula Srivastava. She is a Hisabush research professor at the University of Bonn and the Max Planck Institute for Mathematics. Dr. Srivastava's research focuses on our harmonic analysis, covering topics such as Fourier integral operators and maximal spherical operators. She will soon be visiting the University of Edinburgh, and today she brings us a talk titled Counting Rational Points Using Harmonic Analysis.
Should I?
Let's
Maybe I can start then?
Yes.
Okay.
Excuse me.
Yes, please.
Thank you for the introduction and thank you for the invitation to speak here. It's a pleasure to have this opportunity to connect with so many fellow mathematicians from so many different places. So as said in the introduction, I am a harmonic analyst. I don't know number theory, but today I'm going to talk about counting rational points using harmonic analysis. This is a field that I've started working on in very recently, meaning in the last 1 or 2 years, since the last year of my PhD. And initially, I was a bit scared into entering this field because, as I said, I am not a number theorist. But what was very pleasant for me to realize was that underneath, I mean, when you in these kind of counting problems, there's actually a lot of harmonic analysis hidden inside. And once you reframe the problem in a particular way, I was very glad to find a lot of familiar topics that I've seen before. And I was very happy to see that the tools that I have learned in my PhD while working as a harmonic analyst could be utilized to solve problems in other areas which people care about. So hopefully I can give you a flavor of that. I will try to not go too deep into the actual proofs, but just to give a flavor of what's the question, why one we might care about it, and how does geometry come into the picture, and then a bit of how oscillation enters the picture. So let's start. Right. So as I said before, the basic theme that I want to convey today is that given a counting problem, there's often harmonic analysis lurking right under the surface. So maybe some of you might have heard about decoupling, which is now already a few years old, but this was a deep theorem in harmonic analysis, but the application of decoupling on the moment curves was the solution for Winogradov's mean value theorem in number theory. Then there's also the classical circle method, which has been used for a lot of time in the problem of counting lattice points. And very recently also, there have been some very exciting breakthroughs. For example, the Guth-Maynard improvement or new large value estimates for Dirichlet polynomials. And maybe you have heard of some of these things or not, or maybe after the talk, you can try looking for some of those. But what I want to say is that this connection between harmonic analysis, oscillation, and counting problems I'm not claiming that this connection is something new. It is well known before. So what I want to talk about today is a different kind of counting problem. This is just to give a bit of motivation of where I'm coming from. And what we would see is an interplay of counting, geometry, and duality. I don't think I will have time to explain exactly what this duality means, but maybe I'll try to give a hint at the end. And where I come from in my PhD, I was learning a bit about oscillatory integral methods. And basically, oscillatory integral techniques have been successful in attacking the kind of problems I'll talk about today, exploiting cancellation and actually being able to count what I want. But what do I want to count? A motivation on a very basic level is counting solutions to equations, integer solutions to equations. So for example, let's consider this, this simple equation. I want to count the number of integer points of this equation a1 square plus a2 square equals q square. So right now I see there are 3 variables here, and I want to see how many 3 tuple of integers actually solves this, this problem. I mean, these are just the Pythagorean triplets, right? So, but if I want to introduce geometry into the problem, rather than just looking at a number theoretically, well, what am I trying to count when I count the number of solutions of this equation? Well, this, if I just look at it not as just integers, but as a function of real variables, this is just the equation of a cone, right? And basically what I want to do, I mean, okay, it would be a double cone and there is a bit of a pointiness at the origin. Let's not worry about that. But what I know about the cone is that this is a very nice geometric surface, and counting the number of solutions of this equation essentially translates to counting the number of lattice points which lie on this cone, this nice geometric body surface that I have over here. Okay, so this is about counting lattice points, which is again a very well studied and hard problem. But let's try to reframe this problem slightly differently now. The equation that I have over here is a homogeneous equation of degree 2 on both sides. What that means is what I can do is I can maybe divide, what I will do is I'll divide both sides of the equation by q squared. And if I do that, then, I mean, another way of looking at this equation is counting the number of solutions a1, a2, aq of this equation, which is now framed in terms of not of integers, but actually fractions or rational points. So now what I'm trying to count is the number of fractions, meaning two-dimensional fractions. So I have two numerators, a1 and a2. And when I say fraction, I have a denominator q. So it's again a 3-variable problem. But now what I've done is I have reduced it into a problem in the plane in some sense, because now I'm counting the number of fractions which satisfy the equation of a circle, with this equation, which is exactly the equation defining a circle in the plane. So the same problem now can be reformulated as, okay, can you count the number of fractions which lie on the unit circle or circle in the plane? So this is the kind of problem I would be interested in, a counting problem I'm interested in, which involves counting fractions, which lie on some nice object. In this case, it's a circle, but you can think of a nice curve or your favorite hypersurface like a parabola or a paraboloid. However, what I should say is this is a one-dimensional object in the plane. It's very singular, right? It does not have any area. So counting the exact number of lattice, fractions on this circle is a very, very delicate and a very hard problem. Let's give ourselves a bit of margin of error over here. And what do I mean by that? Well, for me, if I want to count exact number of points lying on the circle or estimate it, that's hard because it's a very thin, it's a zero measure object. Let me thicken the circle a bit, which is something we often see also in harmonic analysis. We thicken things, not single objects that we want to look at. And now I say, okay, instead of counting points lying exactly on the circle, let me give myself a margin of room. Let's call it delta. And then try to count the number of points which lie within this error margin of the circle. So this would, and in fact, it's not delta, maybe I should say delta over q, because 1 over q is in some sense, a natural scale to look at when I'm looking at fractions with denominator q. So now what am I counting over here? I have given myself made the problem slightly easier for me. I want to count the number of fractions lying in a delta over q neighborhood of my circle. So now I'm not counting rational points on this object. I'm actually counting rational points near this object. So there's a difference, and I'll talk more about why this difference is important in a bit. But this is the problem that I'm interested in. The circle is a very nice manifold, but we will not restrict ourselves just to that. We will look at it in a general setting of manifolds. So what's the problem that we want to look at today? Let's suppose we have a compact submanifold in our ambient space. Suppose the dimension of the manifold is D and its codimension is M, and it's immersed in the ambient space of total dimension D plus M, right? So the example I showed you before for the circle in the plane, the dimension is 1 and the codimension is 1. You could maybe take a sphere in our N, so then the dimension is N minus 1 and the codimension is 1. Hypersurfaces are nice, but I also want to not look at problems where the code dimension might be even higher. So this is the most general setup. But again, I want to look at manifolds which can be immersed at least locally in a Euclidean space, because I would be using Euclidean harmonic analysis techniques here. So as we say, the question we want to ask is how many rational points with denominator of a certain size, which in some areas is also known as the naive height of the fraction. So how many rational points with denominator of a certain size lie in a small neighborhood of my manifold? So now there are two parameters here that I need to define. One was the delta that we saw earlier, which will measure how close I am to my manifold. And the second is this, what you here see is a big Q, which measures how big the size of my denominator is allowed to get. Because, if I don't put a condition like that, the number of rationals are infinite, right? So, of course, the answer would always be infinite. So I always take something with a bounded denominator size lying at a certain distance from my manifold. And the distance is governed by delta, but I just normalize by the size of the denominator Q. And as I said, think of delta as something small, like some line between 0 and 1/2. Okay, because if you take delta e to be 1, this will always have a solution. Like you can always find a fraction, any point on the manifold, you can always find a fraction with denominator Q which lies within distance 1 over Q. But as you make the delta smaller and smaller, that's when the problem gets non-trivial. Okay, so this is the question I want to answer. Now, before we set about actually talking about, okay, what are the results, let's try to get a feeling for this. And in particular, what's a good guess for this number, right? And the answer I want on my counting function is some kind of a formula or estimate depending on delta and Q. And the implicit constant should not depend on them. There should be an explicit dependence on delta and Q. Okay, so we'll get to the so again, if you want to think about some examples, at least in the planar curves, the circle we already saw, you could also think of the parabola and trying to count the number of rational points in the neighborhood of the parabola. Or in the higher dimensional case, you could think about the analogs of this would be a paraboloid, which is again a very nice curved hypersurface with non-vanishing Gaussian curvature. If you want to think about manifolds with higher codimension, well, the most difficult case would be the case of a curve, meaning something which is of dimension 1, so very, very thin, that has dimension lowest possible. But, still, so a curve to think about would be, for example, the helix. So the red curve over here is a circle, it's a planar curve. And in contrast, the helix is something which is which has non-vanishing curvature and torsion. Okay, so these are the kind of manifolds that I want to think about. But now let's try to reformulate my problem a bit. I want to think about everything in terms of smooth manifolds, which are locally immersed in this ambient space. So what I can do is I can actually, in this case, I can think of my manifold. It's a compact manifold, and it is locally, I can parameterize it in this way. So if it's a d-dimensional manifold and has codimension m, then the first, I can parameterize it so that the first d coordinates are free. They are under my, I can choose them. That's my degree of freedom, d, which is the dimension of the manifold. And then I have the codimension f, which is the final m coordinates depend on the first d coordinates in some way. That's the codimension. So I have the first x d coordinates which are in my hand, and then the final m coordinates are given by these functions. By this function f, it's not a single function, but a tuple of m tuple of functions. Remember, m is the codimension of my manifold. So And I'm thinking of a compact manifold. So what I can think is that my manifold is just parameterized, maybe say just over the d-dimensional unit cube. So that's a compact thing, just to make life easier for this presentation. And so the manifolds I'd be looking at would be of this form. So, and then remember, this was the counting function that I want to look at. So the number of fractions, d plus m dimensional fractions, because that's the dimension of my ambient space, where the denominator goes up to big Q, and the distance of these fractions from my manifold is delta over Q. But now that we have this formulation of my manifold, let's if my manifold is parameterized in this way, I can reformulate the problem, not in terms of the manifold itself, but in terms of this embedding, in terms of these functions. So let's see how that is done. Basically, instead of counting the nm, I would be counting I will be looking at a new counting function called nf, which up to constants would be the same as the previous one. Basically, counting fractions, d plus m dimensional fractions in a delta over q neighborhood of the manifold is the same as saying, okay, the first d coordinates are in I have the freedom to choose them. So if I choose the first d coordinates, so this is to be a fraction of denominator q. So this is the first part that you see over here. So now p over q is a fraction, d-dimensional fraction. That's the first d coordinates that I choose. If I choose that to be my first d coordinates, how far are the last m coordinates away from being fractions with denominator q themselves? And my measure of how far is delta over q, right? So this is what I look at. So again, I choose my first d coordinates. Since my manifold is parameterized over the unit cube, the numerator has to be bounded by the denominator so that p over q lies in the unit cube. And then what my condition is that the size of the numerator should be bounded away by the size of by q. And then the non-trivial condition is type what are the last m coordinates? They are simply the fraction p over q plugged into this m tuple of functions. And how far are they away from being fractions? L over q of denominator q, and they should be less than delta over q. So that's this last condition over here. But once you write it like this, what you can do is you can clear the denominators, and then what you get is basically you multiply both sides by q, and now you're getting a condition which is measuring the distance from the nearest integer of q times fr p over q. So that's how I've reformulated it now. So now, so this is the definition of the counting function that I will work it with, because now I can try using the properties of the function f. The properties of the function, of course, are governed by the geometric properties of the manifold, and try to say something about this point count. So these are the three conditions that I keep in mind, and this is my counting function that I would have. And with this definition of the counting function, you don't need to remember it. I'll recall it when we need it. What is a good guess to have for my counting problem? Okay, so what would be the trivial count here if this is the thing I'm counting? Well, the third condition, which involves the delta over here, is the most non-trivial one. Let's forget about that for a bit. All right. So what I'm thinking is, so I take delta to be 1, which is the most trivial case, or say 1/2. So that for every choice of the first d coordinates, I will have more or less just one choice of the last m coordinates if I do that. So then what is the maximum number of fractions that I can count? Well, the number of choices I have is essentially the choices for the first d coordinates. Now, the first d coordinates are given, so I have, because both the numerator and the denominator are bounded by big Q, I have about, firstly, big Q many choices for the numerator. And then for each choice of the numerator, I have about q to the power d many choices for the denominator. So all in all, if I end up counting everything, forget about the last condition, I will count q to the power d plus 1 many fractions around my manifold. That's like the thing you get if you just forget totally the structure of the problem. And what I want to do is want to be able to do better than that, or at least try to identify a nice class of manifolds where I can do better than this so-called trivial count, because I want to see the dependence on delta as well. My intuition would be that for most nice manifolds, if I get closer and closer to my manifold, meaning the delta becomes smaller and smaller, then the rational point count around the manifold should also get smaller in some sense, meaning that this function should depend on delta too in some way, right? That's a natural thing to expect. However, I have to really see what kind of manifold will give me that, because there are some manifolds for which this is the best you could do. For example, if your manifold is completely flat, then no matter what delta you choose, whether you're far away or really close to the manifold, you will catch all of these points on your manifold. This is because all of these points will lie on the manifold. It doesn't matter if you're far or not. There is no dependence on delta. And that's and what this example tells us is that flatness keeps us from getting better estimates over here. And this is an enemy which also often crops up in harmonic analysis. We have some nice decay estimates which we get for spheres, for example, or circles, which we don't get for things which are flatter. So the picture you should have in mind is something like this. Uh, if your plane, for example, totally aligns with the lattice formed by your rational points, then a lot of these points will lie on your plane completely, and then basically you catch everything possible. So this is the situation of complete flatness that I want to avoid to be able to get some better estimates for my counting function. Okay, so let's go have a go at it again now. Suppose I want to, again, I have my counting function on top, and I want to count what is a better count that I could expect. What the previous example has shown me is that I have to assume some kind of non-degeneracy condition of my manifold. Now, I have intentionally left the word non-degenerate vague here. I don't really want to get too much into the details of what that might mean. But what the picture should have in mind is non-degeneracy should disallow this property that your manifold is completely contained in something which is flat, is contained in something which is totally flat. Okay, so it should be non-flat in some way, but it's still you should still think of it as some very mild condition on the geometry, and we'll talk about that in a bit. Okay, but suppose your manifold is non-degenerate, for which I could expect. Okay, so in this kind of geometric setup, what is a reasonable guess to impose on this point count? Well, as supposing that the world was totally uh, fair and everything was random, what I would expect is this. Well, if I counted everything, what I've seen before is I would count q to the power d plus 1 many fractions, where d is the dimension of my manifold. But now I know that in delta of the directions, in m of the directions, these are the codimension of the manifold, I'm only looking at a neighborhood of size delta. So assuming in an ideal world that if the fractions were in some sense randomly distributed or uniformly distributed in the neighborhood of this manifold, I would only expect delta to the power m, delta many, to catch delta fraction of the delta proportion of this total point count, right? And so delta for each of the codimensions, and I have the codimension of my manifold is m. So probabilistically speaking, what I would expect is to count delta to the power m times q to the power d plus 1 many points. So this term over here was if I had counted everything, forgetting about the last condition. But otherwise, if I do allow for this, if I do assume that the number of rational points in the neighborhood would roughly hit delta many times, because that's the radius of my neighborhood, then I would expect only a delta contribution from each of the codimensions, and that's why I get delta to the power m over here. So this would be a significant improvement over the trivial count that we saw for smaller values of delta. Well, very good. But can we expect something like this to hold for all values of delta, no matter how small we take delta to be? Well, that's not quite true. this heuristic that we have, which is a very random probabilistic naive heuristic, can't be true really for very, very, very small values of delta. Because if it were, we could always take delta to be zero. When delta equals zero, this term, if this heuristic was always true, delta, it's telling us that when delta is zero, the number of rational points is actually bounded by zero, right? The term over here becomes zero. So basically, what this says is that if this heuristic was always true, it's saying that provided my manifold is non-degenerate, there are no rational points lying on the manifold, because delta equals zero is counting the number of rational points which lie on the manifold. But that's not something we can really expect to answer, right, for a large classes of manifolds, because the geometric considerations like we are looking at today can only predict what happens in the vicinity of the manifold. But what happens right when you're on the manifold is not just a feature of the analytic or geometric properties of the manifold. Right on the object, what the properties which become more important are the properties of the object as a variety, the algebraic nature. And of course, I mean, there's a lot of people working on getting exact counts for counting rational points on varieties, or even integer points on varieties, right on. So just the kind of techniques we are going to use today, we would not be able to predict the number of rational points lying right on the manifold exactly. However, what we still hope to do is predict it to a large degree of accuracy up to a certain critical threshold of delta away from the manifold. So how do we kind of get a benchmark for what that critical threshold should be? We can look at some nice examples. For example, like the sphere in RD, sphere SD in RD plus one, and try to see, okay, how many these are objects for which, through circle method, for example, we know how many rational points lie on these spheres, and the good guess seems to be is q to the power d. So we know that even if we have some nice geometry, we can expect to count as many as q to the power d many points on the sphere. Maybe there are no points on the sphere. We don't. It also depends on other properties, but there can be as many as q to the power d many points on it, which irrespective of even when delta is zero. So in order to be, so what this tells us is the first term over here should dominate when we are sufficiently away from our manifold, and this second term that I have, this error term, would dominate once we are close to my manifold. And we can compare these two terms and see where does the first term dominate. That's the critical threshold of delta, at least what we expect. So the first term dominates. I mean, this is just a simple game. You just compare exactly when delta is bigger than q to the power negative 1 over m. Let's give ourselves an epsilon of room. So what's basically this is saying that provided delta, so q was our upper bound on the size of the denominator. So provided our delta is bigger than q to the power negative 1 over m, where m is the codimension of my manifold, I do expect the first term, this probabilistic heuristic, to hold true. And this gives us, and as I said before, this term is the term which came because of the random heuristic that we discussed, a naive idea. But let's try to what you should keep in mind is there's really a difference between counting points on the manifold or on an object versus away from it. And we will be, or versus near the manifold. And we are looking at counting rational points near the manifold, meaning above this critical threshold of delta. And below this critical scale, what is more important is algebraic considerations for varieties, which is not something we are going to get into, which is not what this topic is about. So, but this gives us the conjecture that we are after. So suppose our manifold is, again, a compact manifold of dimension d and codimension m, which is immersed in the Euclidean space R to the power d plus m. And suppose it is non-degenerate, by which, again, you should mean not completely flat. That's what you should think of. Then I expect the number of my counting function to behave like delta to the power m. M is the codimension times q to the power d plus 1. provided the size of denominator is large enough and delta is above this critical threshold that we saw earlier. All right. This is the big conjecture in this area about counting rational points near manifolds. And the what we would like to basically understand is what is the precise non-degeneracy condition on my manifold for which this conjecture is true. This problem is interesting, at least for me, for its own sake. But if we are able to prove this conjecture, which, by the way, is open, I mean, depending on depending on the definition of non-degeneracy, but this conjecture would have several applications, including a sort of dimension growth conjecture for manifolds and also about different time approximation on manifolds. So I want to very briefly discuss the first of these applications, which might be interesting to maybe some of you who might also be interested in algebra. So basically, what do I mean by this? So again, okay, I have talked a lot about having this difference really clear that counting points on the manifold is different from counting points near the manifold. However, if I get this nice estimate for if I am able to prove this conjecture, and I do get an estimate for the number of rational points near the manifold for this up to this critical scale, well, that also tells me something about the number of rational points lying on the manifold also, right? So if the main conjecture is true, well, it's not true for all values of delta, but it is true for values of delta up to this critical scale. If I do want to count the number of rational points lying on the manifold, that should be this is delta, meaning when delta is zero. I think the rules of zero and Q are switched here. Sorry about that. But well, this formula does not tell me that because it only works up to delta. But what I do know for sure is the number of rational points lying on the manifold should be dominated by the number of rational points within a delta neighborhood of the manifold for a positive delta. And so I choose the scale of delta, which is exactly where up to which this formula works. So I inflate it to the critical scale q to the power negative 1 over m. You can just forget about the epsilon for this talk. And there I do know that if this conjecture were true, I do know what's my expectation at this point, right? Well, I simply plug q to the power negative 1 over m plus epsilon in the place of this delta. So basically the powers of m cancel. I get q to the power negative 1 over here, and that cancels with 1 power of q. So what this tells me is the number of rational points lying on a non-degenerate manifold should be bounded above by q to the power d up to an epsilon of error. But again, d is the dimension of the manifold. If this conjecture is true, this is what it would tell me. Okay, so I do have some estimate on the for a number of rational points on the manifold if I'm able to prove this conjecture. And what that reminds, so this is the conjecture that would be true for the number of points on the manifold. And a parallel one could draw with is the dimension growth conjecture, which is actually in the field of in algebraic geometry. And this is at the level of projective varieties. I don't really want to get into too much into the details. Also because I don't work in this, and this is not something, this is not, again, the topic of this talk, but essentially the dimension growth conjecture in algebraic geometry says that if you have a irreducible projective variety of degree at least 2, then the number of rational points lying on the variety, not manifold, but variety, is bounded in an asymptotic way by the dimension of the variety. Okay. And then, so there a lot, I mean, I call it a conjecture, but it's not really a conjecture. It's actually, so B here over here is playing the role of Q. That's the height of my, of the rational points lying on it. So, and this is essentially, this is not essentially, this conjecture has essentially been proven by Selberger because up to this log error, he proved it with an epsilon, but then now there are also refinements. And let me say that this upper bound that is there in this conjecture is actually sharp in general, but if you put more strong assumptions on your manifold, on your variety, then you can hope to do something better. So this is some nice, I would say, analogy. So, I mean, you have this dimension growth conjecture coming from the point of view of an algebraic variety, and you see that there's a conjecture about the counting rational points near manifold, which would also give you something similar. Except now the dimension over here is corresponds to the dimension of your manifold, right? Not the variety. Anyways, uh, so this is one thing, but let's come back to the big conjecture that we had established and try to see what we know about here. So for this, there have been several exciting breakthroughs in the last 12 years. And what this conjecture says, so I have the still notation. This basically means just like asymptotically, you should have the number of rational points should be bounded above and below by this term times a constant, which depends on manifold, but not on delta or Q. So, but there are two aspects of this conjecture now, right? I mean, one, might want to prove the upper bound for the counting function is of the order of delta to the power m times q to the power d plus 1. And on the other side, might want to prove that the lower bound for your counting function is also of the same order. Establishing lower bound would tell you that provided you are a certain critical threshold away from your manifold, you do have you do count the number of points that you would expect to count because of a random heuristic argument. On the other hand, the upper bounds would tell you that this is the maximum number of points that you would count in the vicinity of the manifold, provided you are away from this critical scale, right? So for the lower bounds, they have been established. So there's for manifolds. So the expected lower bound has been established for manifolds under very mild non-degeneracy conditions, geometric conditions. However, on the other side, for the upper bound, some upper bounds are known, and we would see in a bit, but there has been more success under strong geometric or curvature assumptions on the manifold. So we would see that. And today's talk, what I want to tell you is that provided if we impose very, very rigid geometric or curvature assumptions on a manifold, we can actually even push past this barrier that has been in this conjecture since a long time. And what I would show you today is one example of a nice class of manifolds where, in fact, one can establish the expected asymptotics at a scale of delta, which even pushes past this critical scale that we see for non-degenerate manifolds. Now, since I've been talking about non-degeneracy and geometric assumptions, maybe I should say what I mean by these smooth conditions versus not. So basically, as I said, when you should think of non-degeneracy, you should think of something which is not completely flat. So it is not contained in a proper affine subspace. And one reason we believe that the big conjecture might be true is because if your manifold is non-degenerate plus analytic, then these lower bounds have been established in the conjectured range of delta. This was a deep theorem of Victor Beresnevich from 2012, where he did show that the expected lower bounds are true in the conjectured range of delta for manifolds which are non-degenerate but also analytic. But his methods don't use harmonic analysis. They use more the geometry of numbers. But what last year, my collaborators, Tamara Schindler, Nicholas Teschner, and myself, what we were able to do was also establish the desired lower bounds, not just for analytic manifolds, but actually smooth manifolds. And in fact, our methods do go beyond this barrier just for the lower bounds. Because we get a different critical scale here, which is better than the usual critical scale for certain regimes. Good. But those results are just in the case of non-smooth, in the case of very mild geometric conditions. Let's talk about upper bounds where we would need more strong geometric conditions. So what is that? So suppose so let's look at the case of hypersurfaces, and that too in the lowest dimensional setting, meaning in the planar case, which is when we are in the case of curves. So think of a circle or a parabola, for example. And in that case, this is what the conjecture would look like. The codimension is just one, and the dimension is also one. And for planar curves with non-vanishing curvature, so which is a much more strong assumption than just saying that it's not completely flat. It's much stronger. The conjecture was all established almost optimally by Huxley. We are using determinant method, but then later Vaughan and Villani established it with for planar curves with non-vanishing curvature, and they established optimal estimates by using Huxley's estimates and harmonic analysis. Great. And one would think that, okay, so now that we know things for the curve, one should be able to generalize it to higher dimensions. But it took many more years, and in fact, just a few years ago, that the sharp result was also established for hypersurfaces, the upper bounds, but with non-vanishing Gaussian curvature, so under a very strong geometric assumption. So this was a result of Zhizhe Huang from a few years ago, and he said that provided your hypersurface has non-vanishing Gaussian curvature, the expected point count, you do get the expected point count in the expected range of delta. Saying that something has non-vanishing Gaussian curvature is very strong setting. So, for example, saying an example of a hypersurface with non-vanishing Gaussian curvature would be a paraboloid, which you see on the right, whereas the cone that we saw earlier does not have non-vanishing Gaussian curvature because the curvature vanishes in the vertical direction. It's completely flat, but it is non-degenerate. So the previous theorem gives the optimal estimate for paraboloids, but it says nothing for the cones. So whereas the cone is non-degenerate of order 2 in our definition. All right. But what is analytic interpretation? So I think I'm nearing the end of my time, but let me just, let me try to bring in the analysis from the geometry. So if I look at my hypersurface, remember, I'm trying to think of my hypersurface as parameterized in a certain way. So now I have the first d coordinates, and then there's only one codimension. So I have the last coordinate over here, which is just given by one function. So what does it mean for me to say now that my hypersurface M has non-vanishing Gaussian curvature? When you look at your function f, that function now is a function of d variables, right? So if I look at its Hessian, which would be a d matrix of dimension d, that should have non-vanishing determinant. In fact, a uniform lower bound on the determinant in your domain. That's what non-vanishing Gaussian curvature is equivalent to. Whereas a non-degeneracy condition of order 2 would just say that this matrix should have non-zero rank. It can, so all but one ranks can vanish and it would still be non-degenerate. But for it to have non-vanishing Gaussian curvature, the determinant needs to have a lower bound. And then finally, now I want to talk about a result that I worked on very recently. So now that we have some strong notion of curvature for hypersurfaces, one might try to think, can one generalize this to higher dimensions, to manifolds of higher codimensions as well? So hypersurface is just codimension 1. But what about back to our general setting of a manifold of codimension M? So what we will look at is what I call a strong curvature condition. So for the non-vanishing Gaussian curvature, I had just had one function, and I said if I look at the Hessian of the function, that should have determinant bounded below. Now I say that if I take any linear combination of, so now I have a manifold of codimension M, so I have an M tuple, and if I take any linear combination of the functions, that Hessian should also be bounded below. This is a very, very strong condition to put on your manifold. In fact, I should say that this condition is so strong that there's only very specific values of the codimension it allows for, which are usually way, way less than your dimension, overall dimension. But let's not worry too much about that. The main thing is this, that this class of manifolds was studied by people, by Shinrei Yamagishi. And a few years ago, what they were able to do was actually establish the expected asymptotic for the point count for this class of manifolds. But the most crucially, they were able to do it in a range of delta, which actually goes below the critical threshold that we talk about. And this was the first such example where this was possible. And this was because of the strong curvature condition that they had. Okay, great. So now we have this example. Can we do better? And so this is what I looked at. And earlier this year, what I was able to do was realized that will prove a result which says that provided you look at the strong curvature condition for a manifold, you can go even beyond. So in fact, the expected conjecture is true for in a range of delta, which is even below the critical threshold, which is even below what Chinla Yamagishi had. In particular, it is even better than what is predicted by the general conjecture for non-degenerate manifolds. And this is the result I have. Don't worry too much about the exponents. The main point is it beats the previous exponents and the expected exponent, which is 1 over m for the range of delta. Okay. And what this gives us is a better estimate for the number of rational points lying on the manifold, which beats what is predicted by the dimension growth conjecture just by plugging in the values. So I'll not talk about that. And finally, what I want to very briefly say, so I wanted to explain maybe a bit more, but it's fine. Basically, I just want to tell you how harmonic analysis comes in. Well, for harmonic analysis to come in, what we first need to do is smooth the counting function out. And then so the counting function right now just measures, can be reformulated in terms of measuring whether your counting function lie in a certain characteristic set. You just smoothen those out using the bump functions. And then Fourier expand it to obtain an exponential sum. Actually, you get an exponential series, but you can cut it off at a certain point beyond which you just get errors, which are okay. So that's how exponential sums come into the picture. But the second step would be, and this is again a standard step in these kind of problems, I want to utilize oscillatory integral techniques. So what I want to do is convert the exponential sums into oscillatory integrals. The way I do it, this would be, and by oscillatory integrals, I essentially mean Fourier transform. And the way I would do it is by Poisson summation, which converts these exponential sums to oscillatory integrals. And these oscillatory integrals actually, so now once I have a lot of oscillation, I want to obtain some this oscillation is what I would capitalize on to get some cancellation. And this is where the harmonic analysis comes in. So once you have the exponential sums or the oscillatory integrals, you can try using the cancellation of the phase to be able to get some nice estimates for your counting function. And for those of you who work more in these techniques, what I use is actually the steep tool called stationary phase expansion. And in fact, I don't just use the estimates, but actually the full-on expansion, in some way allows me to go to a dual counting problem. And this kind of dualizing is actually some kind of an involutive process. So you keep doing going to the problem, you get to a dual problem, you repeat the step again, which leads you back to the original counting problem. And somehow you bootstrap to be able to get some nice estimates for your counting function. So if I had more time, then I would have told you more about the proof, but this is something expected. I just wanted to give you an idea of what this happens. So basically, you take the counting function, you write it in terms of the characteristic functions, and you smoothen it out using bumps, expand it into a Fourier series. And then when you do, there's one term where you would, at the zeroth frequency, you would have no oscillation. That's where your main term will come in. And the main key thrust lies in taking these exponential sums and trying to exploit oscillation to show that the contribution from these exponential sums is also the expected one that you have, the main term, so that the main term is the one which dominates. And this is where curvature is crucial because we have stationary phase, which requires non-vanishing Gaussian curvature. The question is how to do it for manifolds of higher codimension, which is where new techniques needs to be developed. But I would rather not get into that for the purpose of this talk. And I'll try to end here. Thank you for your attention.
Thank you. Thank you so much, Rajula. Like a compilation book of our speakers' response, we would like to hear your perspective as a mathematician. How do you perceive the challenge faced by women in community when trying to establish themselves in academia?
Okay. Thank you for the question. Should I stop sharing or?
Yeah, please.
Okay.
So the question is, how do you perceive the challenge faced by women in the community when trying to establish themselves in academia?
Yeah, so also being a woman of color myself, uh, of course, the challenges are there, and there are some very institutional strong challenges, which all of us have faced. And then there are also some subtle ones. Maybe that's what I can touch upon a bit, which is I feel like one challenge which women or any member of an underrepresented community feels is this constant need to prove ourselves to people to be taken seriously. And in order to just get to the same position, you don't get, sometimes you might feel that you don't get the same benefit of the doubt that might be provided to other more privileged or more represented sections, just because they might be more represented, so there are different groups of people who identify with them. So that's a challenge which I feel is often there with us, and I think it never really goes away, because you always feel this need to justify where you are, and that you do deserve this spot. But I think what helps with it is having this, as you keep going forward, you do find people who are willing to bat for you, willing to advocate for you. A lot of this are other fellow women or senior women who have themselves faced the same issues. Some of them might also be men. And having this, not everybody would, of course, these are people you meet few and far between, but once you meet them, these mentors, it's good to have this kind of support uh, of and group of people who are willing to advocate for you, and with whom you feel like you don't have this constant mental struggle to keep pushing for yourself. They just take you as you are and trust your abilities. So I think that is something which has helped me. But yeah, on day-to-day level, I think this challenge is always there to feel like you belong, or to always prove that you deserve a spot. And I think one thing which I'm still learning, but maybe it's good to share, is that it's good to be your own advocate as well. So don't be afraid to put yourself out there. And if there are opportunities, maybe you feel, because I think us women have this tendency to feel that we are not good enough for things, so we might not as well not apply. Maybe just go ahead, put your name in the hat, and then see what happens. So advocate for yourself as well.
Okay, thank you so much for your question. Okay, now we open the regular question session. Is there any question or comments? Let me check. Duval? Yes?
It's not, first of all, just first a comment and later my question, right? First of all, Rajula, thank you very much for sharing this perspective, answering this question of Karina, which is very important for us. Let's say that women mathematicians share their perspectives, right? That was first comment. Second comment is more about your presentation. First of all, thank you for you are doing very serious research, and it's very nice to see these impressive results. I would like to ask about this strong curvature condition that you mentioned at the end. If you can think about it, about which kind of manifold satisfy this, and how much important it is for your work, right?
Yeah, thank you for the question. If there was more time, I think I was a bit slow in the beginning. I would have liked to speak more about it. Right, the strong curvature condition is very important. Unfortunately, like I showed a few pictures, but I feel like the picture I wanted to show of this condition, it's very hard for me to visualize it and to show it, because you see the strong curvature condition only first of all for manifolds of codimension 2 or higher, because it's not just about the curvature in one of the functions, but about these families of functions together. So what it's in some sense it's saying, and because of the restriction on the codimension, the first case in which you'll see this condition is, for example, a manifold of dimension 4 and codimension 2. So maybe for some of you, because or the one you since you have looked a bit on Heisenberg type groups, this is a condition which is exactly there for Metivier groups, right? Of course, it's not the same thing, because for Metivier, if you have worked on it, that's one place to see. And there, it's a different setting over there, because those are anti-symmetric matrices. These will be symmetric, but because they are Hessians. But the thing, how I like to look at it and how I've used it in my proof is that having just curvature for one function allows you to do stationary phase, but having this combination, this non-vanishing determinant condition for the combination of the functions is somehow saying that not only do you have curvature in each of these individual codimensions in some way, like when you look at the projections, but somehow, if you look at the functions as a whole, there is some cancellation, there's some nice curvature condition happening there, like because we know in higher code dimension things can go wrong in a variety of ways with curvature, and this condition is saying that that is not happening, and that's why it's such a special condition that you don't really see it that often, but when it does, you can really utilize a lot of the cancellation. And in fact, I mean, I want to point out that this condition in particular is saying that if you project it down to each of the codimensions individually and freeze the other components, you do get non-vanishing Gaussian curvature. So it's something like you have a manifold whose sections have non-vanishing Gaussian curvature in different ways. And that's what the Schindler Yamagishi use. So they reduce it to a hypersurface problem and they just use Huang's result for hypersurfaces. I mean, there's not just that, there's more happening there, much more, but yeah. But I thought that in their method, they were not able to utilize this curvature between the codimensions as well. And which is what, if you utilize, that's what in some sense allowed me to go do better. So it is a very important condition.
Thank you very much. Very
thank you
impressive
for the question.
research, of course.
Thanks.
Thank you, Luan, for your question, and thank you, Rajula, for your answer. Let me check if we have more questions, maybe on the chat. Okay. Okay, we don't have more questions. Okay, so thank you so much for your very
Thank you
nice
again
talk.
for having me.
We will continue with the next speaker. So, Milton,
Okay.
you can do the presentation. Thank you.
Okay.
Hello. Yeah, can I share my slides? This is Masha. Yeah.
Thank you very much, Dr. Srivastava. And now, it is my honor to introduce Professor Maria Gordina. Professor Gordina is a distinguished mathematician and faculty member at the University of Connecticut. Her research reads stochastic analysis, geometry, and functional analysis, and she has been recognized with numerous accolades, including a Simon Fellowship. She is also a member of the American Mathematical Society. Today, she will present her talk, Stochastic Analysis and Geometry Functional Inequalities. Please join me in giving a warm welcome to Professor Gordina.
Thank you. So should I start or should we wait a couple more minutes?
Okay.
Should I start or can you hear me?
Yes.
Yeah.
Just maybe, so maybe
Couple of minutes.
maybe
Okay,
a couple
that's
of
good.
minutes to start
Yeah.
at 2 p.m. And on the meantime, maybe Karina, maybe you can ask to Professor Masha Gordina the question.
Okay.
Yeah. Thank you for
So
the
we will-
introduction, I should say, yeah, first of all, yeah. Thank you for the invitation as well. Yeah. Karina, yeah.
Yeah, thank you so much. So we will take these minutes. So before you start, Professor Gordina, it's my pleasure is here in front of you, virtual, but okay. So could you share with us how you became interested in mathematics? At what point in your life do you decide to pursue a career as a mathematician?
Thank you for the question. Yeah, so I'm originally from Russia. I grew up there and I got my undergraduate degree there. And my father was a mathematician, but this is not maybe, I'm pretty sure it played a role, but this is not how I became a mathematician. I was supposed to be a classical musician playing violin. and I'm also Jewish, and at the time it was not easy for Jews to get to university, but I was very attracted to math when I was in school. I was disciplined in math circles, and so finally I decided to pursue this career. And so I would say that it started very early in school, and yeah, and there were lots of opportunities to pursue math, and I'm quite happy I'm doing it. I hope I answered the question. Yeah.
Yes, thank you so much. Okay, so you can start now, please.
Thank you. Thank you very much for the invitation again. And I think the topic of my talk will be quite connected to the previous talk with a very different take, and it will be more of a survey talk. So I'll try to connect several different fields and explain. It's really, there will be some recent results mentioned, but it will be more an overview of what we have. So please interrupt me if you have any questions, because I know this online talks I'm out of practice now in the last year or so. But yeah, it feels a little bit isolating when you talk to this outer space, right? So please, if you have any questions, I will try to keep my eye on the chat and interrupt and ask questions. So what I want to do is to look at how geometry plays into what we call functional inequalities, and I'll give you several examples of such inequalities. So on this slide, you see the names of very classical inequalities: Sobolev, Poincare, Harnack. Sobolev is in green because that's what we'll concentrate on. So this is inequality that relates LQ norm of functions with the gradient norm here. And as you can see, the constant we have here is significant. So yn here is in red because it's the dimension of the underlying space. And since, at least in the beginning of my mathematical career, I was very interested in things that actually something like this in infinite dimensions, this kind of dimension-dependent constants really occurs there. So we'd be interested in this kind of inequality. So functional meaning functions on whatever the underlying space is, and some type of inequality like this. And we want to know how constants depend not just on LP, P in that exponent, but also on the dimension. So why mathematicians are interested in these inequalities is because we use them to prove existence or uniqueness for PDEs. We also use them for establishing regularity of solutions, right? Because here you control LQ norm on the left by LP norm of the derivative on the right. And it's related to spectral properties and so on and so on. So what we want to do is we want to also look at where, the case when we replace the underlying space here, the Euclidean space, by something like Riemannian manifold that has curvature, for example. Or we want to replace Laplacian, the usual Euclidean Laplacian, which is present here, even though we don't actually mention it, by something like an elliptic operator, and later even by something that is not elliptic operator anymore. So as I mentioned on the slide, I will not go over all the bullet points, but I mentioned here some more classical methods of how people approach this kind of inequalities. So for example, Moser's elliptic Harnack inequality is using Sobolev inequality. So we have different classes of these functional inequalities, and they're all related in some form. Sometimes you want to have some kind of condition on your underlying space, such as here I mentioned that you say have a metric space, not only a Riemannian manifold, and you have some control over volume growth of how the volume of metric balls behave. And that allows you to have something which is easier to prove, like Poincare inequality, which I don't mention here, like spectral gap type thing. And that implies stronger Sobolev inequalities. There are all kinds of different things, including the famous Nash inequality that we will not talk about in this talk. They are often equivalent to heat kernel upper bound. So which means that if you can solve the heat equation and have some kind of bounds on those solutions, that allows you to prove functional inequalities, or you can use functional inequalities to know some bounds on the heat kernel. So this appears in lots of applications, not just in analysis and probability, but also in geometry. Of course, heat flow is something that appears in lots of applications there. Again, we'll not talk about it. And the spectral properties here, I only mention the Schrödinger operators, but also we have recent work on Dirichlet forms where we also use it for operators restricted or to like metric balls, and then you want to look at the boundary behavior of this kind of operators without having PD theory. So lots of applications, and it's a very active area of research, mathematical research. So one of the applications, at least from the point of view of probability, is what we call Markov semigroups. And there you can replace not only the space that you look at here, Rn, but also the measure here. And quite typical is the choice of the measure to be an invariant measure of this Markov semigroup, which physically usually means usually meaning under certain conditions, as I mentioned here, ergodic properties, meaning that it's this stability of this system, or ergodicity, meaning that you hope that as time goes to infinity, the system actually approaches the state which is described by this invariant measure. So geometrically, what these function inequalities are related to are the geometry of the underlying space. If it's Riemannian manifold, then you might have some curvature bounds, such as Ricci curvature bounds. Metrically, you can talk about volume doubling. So it's how the volume of metric ball behaves when you double the radius, right? And if you have control over the ratio of the volume of these two metric balls, then what we call volume doubling. So lots of analytic properties of the heat kernels, for example, can be proven using just these properties. So the methods that people use are also very different. And I'll just talk about a sample of them, but mostly related to geometry. But before going to that, I want to mention this log Sobolev inequalities, which are the inequalities that, as you can see on the right-hand side, remember we had the constant which was using the dimension and p. So p in this case is 2, more or less. And the constant actually doesn't depend on the dimension anymore. It depends on the curvature. So in this case, Ricci curvature bound. So M here is Riemannian manifold. Ricci here is the Ricci curvature bound. And so what you have is Sobolev-like inequality, except it's log Sobolev here on the left-hand side. And the main point is that it's dimension independent. So this was used many years ago, decades ago, by Nelson and Landgraf for applications in quantum field theory, where this dimension issue is significant. So you want the dimension to be infinite in some sense. And for Nelson hypercontractivity, for those of us who are familiar with the concept. So the first proof was for the Gaussian measure on Euclidean space, and it uses lots of properties of the Gaussian measure, but actually now you can prove it using completely different methods, which I will mention maybe a little bit in passing. So I'll start with a very simple example, and I'll give you one proof, kind of simple proof of how you can see how this functional inequalities are used. So let's start with Rn. So no Riemannian manifolds, no curvature present, but instead of the Lebesgue measure, I'll take the Gaussian measure. So it's the Lebesgue measure with normal or Gaussian density. So it's a probability measure. So of course we go from infinite measure to this finite measure case. And what you can prove, and this is really a computation here, and it's actually an equality, not an inequality here, is that if you take the this Gaussian density here, P of x, shifted by an element h here, then you can prove that this LP norm of the shifted density with respect to the original one, with respect to the Gaussian measure, can be estimated. And as I said, it actually is equality in this case. You can compute it, is the e to this degree, the power here, the exponent. Okay, so what's the point here? The right-hand side here doesn't use the dimension at all, right? So it uses only the norm of the shift h and p, which we use for the LP norm. Okay, are we okay with this? Okay, yeah. Okay, so the proof, as I said, is very simple. That is, in this case, we have the Gaussian density. It's written explicitly, so you can compute this ratio here and find it LP norm, and you can just compute and find that it's equality, and therefore you have inequalities also. So what's behind it? Behind it is that unlike the Lebesgue measure, the Gaussian measure is not translation invariant, but it's what we call quasi-invariant, meaning that if you shift it by h, you get a Radon-Nikodym density here, which is integrable, LP integrable, and this actually survives in infinite dimensions. So you can define the Gaussian measure in infinite dimensions, and it still is true that you can shift the Gaussian measure by some h, not every h, and you get this kind of property. Why it's interesting is because in infinite dimensions, of course, you don't have a reasonable Lebesgue measure, right? Translation invariant measure. So Gaussian measure is one of the choices. It's a very reasonable choice because we don't have a good reference measure, but this is one of the most natural choices. So probabilistically, what you do is you can look at what's called Wiener space here. So it's a classical Wiener space here. So it's a space of continuous functions, say on 0, 1, equipped with a sup norm, and you have the Sobolev type space sitting inside of W. So H is a space of functions which are absolutely continuous, whose derivative is in L2. Okay, here. So these are functions H in W, right? So we usually start at 0. I didn't say this, but this is what we do. So why we call it a Wiener space? Because actually it's the space of trajectories of Brownian motion. So probabilistically, that's what it is. So this triple, you can construct the Gaussian measure on this infinite dimensional space, bounded space. This triple is an example of what we call an abstract Wiener space. So H is densely embedded in W, and you usually start with H. This is one of ways to look at this. It's a Hilbert space. You try to construct the Gaussian measure there, and it ends up living on a much larger space W. And the original space here, H, the Cameron-Martin, as it's called, actually has measure 0. So this is something you don't see in finite dimensions. I wanted to bring you this flavor of infinite dimensions here. So how can we use that elementary functional inequality I showed before? You can actually prove a similar type property for the Gaussian measure here. So what this theorem says, and it's a classical theorem, it's not, of course, not my theorem, is that you can shift this measure by h. So of course you cannot do it the way we did before, because previously mu had density with respect to the Lebesgue measure. You don't have this anymore. But you kind of do the integration by parts. You take this h to, it's equivalent to that almost, to the right-hand side to the measure. And what you get is that you have this Radonic atom density here, okay? So you take h to the measure mu, and you acquire this density here, Radonic atom density, and you actually have LP estimate here. So what's the point? What's the point of this theorem is not just you can prove this, but you can also prove that it only happens with the shift h is from the Cameron-Martin, from much smaller space. So if you take an element h which is outside of capital H, this is not true anymore. This is really an infinite dimensional phenomenon. And I will just go very quickly over the proof. The proof here is really using finite dimensional approximations to both Hn and W, which I will not really talk about. So this is when you see Rn that we had before, and you see that the Gaussian measure that we have now is really the same Gaussian measure we had before on the Euclidean space. And then you can use the property we proved before. So you reduce this to Rn more or less here, and you know that that you can see that you can use the fact that you can shift the Gaussian density by Hn, estimate that, and remember what I told you before is that the kind of estimate we had is here doesn't depend on n, it only depends on the norm of this Hn here. And so what you can do now is you can take n going to infinity, and you can see that this norm will approach the LP prime norm of the function on the whole space. And this is only finite if Hn approximates an element from Cameron-Martin space, capital H. This is really a proof of that estimate. And when you finish this, you actually get this, what I mentioned before, where you can see that we can only hope for this kind of property for the Cameron-Martin type shifts, which has measure zero of mu. So this is a very classical application of a functional inequality to prove this kind of property. So why is it interesting is, again, because that gives us a way to prove smoothness of measures when we don't have good PD theory, or we don't have densities with respect to the Lebesgue measure where we can describe the density as a smooth function. So this is really what I mentioned here again. So quasi-invariance of this measure, or this almost invariance, this Radonic atom density of measures in infinite dimensions is viewed as smoothness property of this infinite dimensional setting in the measures. You can also prove regularity of invariant measures or for degenerate semigroups. I might actually get to this later in the talk, we'll see. But it also has other interesting applications, for example, for representations of infinite dimensional groups, which are not easy to come by, but they also have, they appear in lots of physical applications. People are really interested in them. And I explained here how you do this. So if you have a group G transformations acting on some L2 space here, Hilbert space, then you can actually represent this group G on this L2 by doing this. So you take measure mu, you shift x by g. So remember, g is acting. So you think about, say, rotations or translations in even Euclidean space. So it's, as you remember, the Gaussian measure is rotation invariant. Therefore, that would be just one here. But translation is not invariant, but quasi-invariant. So you would get something non-trivial here, not one. So it's a function. And you shift the function f from L2 by g also, or g inverse. So that gives you an unitary representation. You can easily check it's a unitary representation. And people have been studying it for many years. And so it's representation of path groups also is being used, can be used, this approach can be used there. So I only mentioned one paper that I was involved in with Sergio Bovera, Bruce Driver, Pershik, but the subject is quite old, and as I said, some of the applications appeared in physics actually. So these are examples there, but what I want to do is now to introduce more geometry, because as I only mentioned that it's my idea, but I also want to go beyond the geometry that you see in R3 or on Riemannian manifolds. I think the Heisenberg group or H-type groups were mentioned before, so we'll see the Heisenberg group now. So let's take R3. So what I will mention is three different geometries here. So one is what I'll call flat geometry, which is the usual Euclidean geometry. So you can see the usual Laplacian here. It's a sum of squares operator, as we call it. So it's a sum of second derivatives. The corresponding stochastic process is the usual Brownian motion. The measure that we are interested in is the Gaussian measure with, in this case, time parameter t. And what I want to do is I want to introduce two other geometries also in a three-dimensional space. So one is Riemannian geometry. What I can do instead of the usual derivatives, this in the direction of x, y, and z, right? So I have point in R3, x, y, and z, and I can take these vector fields, but I can change them here. And then I can look at the corresponding stochastic process. So I can write it explicitly here. And if you don't know what it means, it's okay. We can write it explicitly later. So this is a solution to the stochastic differential equation. But actually, it corresponds to the Brownian motion in the Heisenberg group, in this case, equipped with Riemannian geometry. So you can write it explicitly. So it's a three-dimensional Brownian motion, standard Brownian motion, as it was the case before in R3. And with a correction term here, which looks very familiar to people who are familiar with, who know the Heisenberg group, because it really looks like a symplectic form, except here it's random. So it uses the Brownian motions. So B1 and B2 are two real valued Brownian motions, independent. So you create this functional of them, which is called Levi stochastic area. So it's a famous functional in probability theory and stochastic analysis. So, and it really looks like the usual symplectic form built on this two-dimensional Brownian motion, okay? So in this case, of course, the measure, again, is has a density with respect to the usual Lebesgue measure in R3. The generator here is different from what we've seen, but it's an elliptic Laplacian, elliptic operator. So finally, and this is a more interesting case to me, is what we want to do is we want to take the same R3 and introduce what's called sub-Riemannian geometry on that. So how you do this, you take the same three vector fields, x, y, and z. So remember, we wrote them in very explicit form here. So this is in global coordinates here. And what you notice is that if you take what's called the Lie bracket of x and y, so you can compute it explicitly in this case, you actually get the third vector field given the z. All other Lie brackets is 0. So what it means is that instead of taking x, y, and z to span R3, we can take x, y, and the Lie bracket of x and y. So what it says is that if we take two vector fields instead of three in this three-dimensional space, and we take all Lie brackets, in this case, the only non-zero one is of x and y, it spans R3, and this is the condition that we call Hermander's condition. I'll mention it a little bit later, its significance, But now what we can do, we can actually put Brownian motions only in the direction of two vector fields here, x and y, and see what kind of stochastic process I get. Remember, I'm still doing probability sometimes, not just analysis. And what it looks very similar to what we've seen before. So it's two Brownian motions. So we don't have a third Brownian motion here. And then we have this Levy stochastic area in the third component. So this really corresponds to this condition, Hermander's condition, that x and y bracketed gives you z. So it's kind of generates the symplectic, random symplectic form here. Okay. So what you see here is that you kind of take a two-dimensional Brownian motion and you use these vector fields x and y to push it through to the whole space, and actually it fills up, you can prove it, the whole R3. Okay, so two-dimensional Brownian motion actually goes in this kind of more horizontal way to span the whole R3 eventually. So why is it different? It's different analytically because the generator of this Brownian motion is sum of squares, but only of two vector fields here, x and y. And it's not elliptic operator anymore. It's a hyperelliptic operator. This is where we use Hermander's condition. Moreover, the measure, the law of this Brownian motion is a smooth measure, meaning it has smooth density with respect to the Lebesgue measure. So we still have the Lebesgue measure as a reference measure. It has a smooth density. And again, it's the result of this Hermander's condition that we have. So we have a bunch of analytic consequences of having this condition, but it also introduces another geometry. It's not Riemannian, but sub-Riemannian geometry. And this is really completely different geometry from what we've seen in the second example. So to summarize this, what we have is R3, which we view as a non-commutative space here with a new product rule here. So it's a group law. You can see here it's the same addition as we have in R3 plus a correction term here, which comes from the symplectic form, right? This is what I allude to here. So it's a symplectic form on R2. We get what's called a central extension here. And we take a flat Brownian motion. Say three-dimensional gives us Riemannian or elliptic Brownian motion. Two-dimensional rolled by these two vector fields x and y gives us a hyperelliptic Brownian motion. And what I want to do is to see the implication of this to the geometry of the space. So what we want to do now is to kind of change it from the point of view that we've seen in the previous talk. So I don't want to just look at the geometry of the underlying space. I want to look at the operator I have, L, which is the generator of this stochastic process also, and see if I can see the geometry of that operator. So this is by now is relatively classical approach, which goes back to Emery and Bakri, Emery, Ledoux. And I'll describe it a little bit just so that we can see, and I'll give you a couple of examples. So suppose we have an operator L, so we'll not pay attention to domains or anything like this. We'll assume that everything is okay here. So they introduce two operators. One is called Pareto-Champ operator or gamma operator, which more or less measures how the operator applied to product is differs from F the operator applied to G and the other way around. Okay, we'll see some examples where you'll see what it gives you at the end. And then you kind of iterate this procedure. So gamma 2 is an iteration of gamma, which will give us the second order terms which correspond to the curvature of these operators. Okay. So the first example is that if you have what we call a sum of squares operators, meaning that it's written as a sum of squares of vector fields xi here, you can actually compute this Carré-Duchamp here, and you'll see that it looks like gradient times gradient, okay? So it really goes to the first order derivative, right, immediately, okay? So you don't see any curvature here. You only see it when you iterate this gamma. So, so I'll give you a couple of examples, because what we'll want to do is curvature dimension inequality, which gives you curvature here in the first parameter, and this is the dimension. So the point of view we want to take is that this is really curvature of this operator L, and the dimension is of the operator L. And I'll give you two examples now where we'll see it. So for the Laplacian on Rn, it really gives you back the dimension of the underlying space. So here's the calculation. So gamma, as we said before, is just gradient or derivative of f times derivative of g, right? I just compute gamma 2 here explicitly. What you can see here is that it's what is called Hessian of f, okay? And this norm here is really the Hessian of f squared, Hilbert-Schmidt norm squared. Okay, that's just the definition of this norm. What you can check here, and it's really a computation that is not that difficult to make, it's Cauchy-Schwarz type inequality here, I think, is 1 over n Laplacian, which is our generator f squared. Okay. So this is really an example, the first example where we see this gamma 2 compared to the operator here. This is what we'll call curvature dimension inequality. And the dimension here is n, and it coincides with the underlying space. As we'll see on the next slide, it's not always the case, okay? So here's another example. So to make it more striking, I decided to take the what's called Einstein-Uhlenbeck process on just the line, real line, and to see that the curvature here will be just 1, and the dimension is always infinite. So it doesn't matter what the underlying space has as its dimension, actually the inequality will be infinite. So the first, you compute gamma, and it's the same as on for the previous operator. So it doesn't see the drift term, as we call it. It only sees the second derivative here. But when you iterate this procedure, you can see that actually the kind of expression you get is very different, and the drift actually plays a role. And you can prove, again, this kind of inequality here. Okay. So this is an example of a much more general curvature dimension inequality that I will formulate now. So the curvature dimension inequality is right here on the right-hand side. So if you iterate your gamma, you get to gamma 2. And if we can find kappa, which plays a role of curvature, and n, which plays a role of the dimension, such that you have this kind of inequality, that is, you can compare gamma 2, you can estimate it from below by the Carré-Duchamp operator squared, and the operator, remember we had the Laplacian applied to f squared, then we say that the operator satisfies curvature dimension inequality with parameters kappa and n. The interesting part here is that for Riemannian manifolds, it's equivalent to Ricci curvature bound being kappa. So what it gives us is a way to replace curvature that I didn't even define by something that we can find just using the operator itself. So it's just purely analytical, right? So you give me your operator and I can find it. So why we care about this when I talk about functional inequalities, because there are lots of techniques for different types of parameters here that imply all these inequalities, functional inequalities I started with. So for example, kappa infinity as for the Einstein-Uhlenbeck gives you log Sobolev inequality. if you have covariance being 0, you get heat kernel estimates or parabolic Harnack inequality or Liao inequality as it's called, and so on and so on. So I give these inequalities here just for the sake of completeness, even though we'll not get to them in this talk. Okay, so the moral of the story by now is that if you have an elliptic operator, usually if you can prove this kind of coaching inequality here, coach dimension inequality, then you can prove a bunch of properties of the corresponding heat kernel or operator itself. And this allows you for, and then function inequalities can be used for all kinds of other regularity results and things like that. Okay, instead of using PDE's techniques directly. So this is what we call the geometry of diffusion operators sometimes. And one of the applications we had of the inequality I started with today, what we call integrated Harnack inequalities, we used it not just for the flat space that I gave you a proof of for, but also for Lie groups, infinite dimensional Lie groups. So this is old result with Bruce Driver, which was published in the Journal of Differential Geometry many years ago, and we proved that if you have this kind of inequality where we have this coach dimension equality with curvature finite, uniformly bound all dimensions, then we can prove it for infinite dimensional groups. And this is what we proved. So the theorem was exactly this. So it's a finite dimensional proof, finite dimensional result. So you can see the right-hand side here only depends on kappa, which is our curvature. There is no dimension here. And the estimate is sharp because it's exactly the same estimate I showed you in the beginning for Rm. The estimate is dimension independent, therefore we applied it to infinite dimensional settings. Okay. So again, it uses exactly the same type result that I had. So I had, remember, x minus h here. So we have a group. So we have this translation by y. This is our heat kernel measure instead of the Gaussian measure. So it's a really non-flat analog of the result I had in the beginning. So then we used it for all kinds of results. And what I want to emphasize here is really the quasi-invariance of measures on this infinite dimensional groups, which allowed us to give very simple or more straightforward proofs for loop and path groups. And so these are paths so these are infinite dimensional groups of paths in, say, compact connected Lie groups, infinite dimensional nilpotent groups like infinite dimensional Heisenberg group, and so on. So lots of results here, and some of this I was involved in, some of them by other people like Ty Melcher. So what happens if you replace the elliptic case by the subelliptic or hyperelliptic case, that is Riemannian geometry by sub-Riemannian geometry? It seems like we use Riemannian geometry a lot, but actually what happens is that the whole straightforward application of this Bacri-Emery-Ledoux type results is not possible. And this is a very simple explanation for this. So if you just follow the same kind of mantra, so you take your operator, which is the sum of those vector fields, squares of these two vector fields x and y, such that x and y gives you z, the bracket to them. And you can compute gamma 2, and then you get this mixed terms, as we call them, and you can kind of see that you cannot control them ever. So there is no hope that you can get something like this kind of an inequality here, which more or less means informally that the coach dimension equality fails. And so you cannot really use it directly, but you can prove something somewhat different for at least some of these settings. And that's what's called generalized coach dimension equality, that was first introduced by Fabrice Boudouin and Nicola Garofalo And in particular, Heisenberg group, the three-dimensional group, actually falls into the framework that they used. So I will not give you details of that, but just believe me that you can prove that generalized curvature dimension inequality. And the interesting part there again is that you can prove that you can prove it without the dimension being present. So the result is that what you can do, you can take setting where there is no rigid curvature bounds, and you can use this generalized curvature dimension inequality to prove a bunch of function inequalities here. And in particular, you can prove the quasi-invariance of this infinite in the infinite dimensional setting, which is really a very typical, very basic example of what you would think about hyperelliptic operator, except that, of course, you don't have the same definition as Fermander used of hyperellipticity. So we really use this notion of smoothness of this, the corresponding heat kernel measure there, and we prove it by using some of these functional inequalities. So this is really an interesting application of this technology, of this technique, and people used two different ways of proving this, and by now there are lots of other examples of where we can use, and by now we have also log-Sobolev inequality in this infinite dimensional setting. So the interesting part here is also that it gives you a good notion of kind of smoothness that would be a replacement of hyperellipticity, and this is really goes back to the original idea of Malavan, who really viewed hyperellipticity in infinite dimensions first, and then if you look at the first some papers of old papers of Heirer and Mattingly, they also talked about different conditions that can be interpreted as infinite dimensional hyperelliptic setting, which has some interesting applications. So in the last several minutes, I'll tell you something about this. So this is very different. I'll just explain why people like Martin Heirer and Mattingly and lots of other people are interested in this. So this is an application to ergodicity that I mentioned in the beginning for the Langevin dynamics. Okay. So this is also an example of an hyperelliptic system, except in this case, it doesn't have subRiemannian geometry to help us. But we still can use some of the techniques that I mentioned before. So what is it? So you have a system of two stochastic differential equations here. So what we like, even if we don't know what this means, let's try to see what we have. So we have P and Q, so position and momentum vectors. So they are both n-dimensional here, P and Q. So you take, so forget about this for now. Okay, so what you have is the usual system here. V is the potential that I'll mention later. Okay, so we are interested in all the parameters we have. So we have friction, temperature here, gamma is friction, T is temperature, and we are interested in lots of different potentials and non-smooth potentials. And then what you do, you add the noise into the system, but what you do, you add it only in half of the dimension, okay? So what happens here is that actually, if you look at the generator of the system, it's also hyperelliptic, but it's what we call weakly hyperelliptic, or it satisfies weak Fermander condition, meaning that you need the GIF term, the one-dimensional, the first order term to actually propagate everywhere. So you need brackets with the first derivative, the term to actually get the Fermander condition. Previously, we only needed the sum of square operators. In this case, it's not enough, okay? So we're interested in the behavior of this system when time goes to infinity. So what do we know about this? We know that it has nice invariant measure, which is this Gibbs measure, which is written explicitly using the Hamiltonian. So the potential here appears, okay? So that's that we have. So at least we don't have this problem. Here the so the questions that we want to look at is the how whether there is convergence to the equilibrium. Usually we know this. We want to prove that it actually is. geometric, and I'll explain what it means. But we also want to know what kind of norm we should take. This is what we mean by convergence in what sense. And we want to have rate of convergence known explicitly depending on all the parameters I mentioned. So to put it in the kind of more physical formulation, I wrote the Langevin equation as physicists would write it as a second order with kind of white noise type thing here. So this would be thermal fluctuations, which still use friction and temperatures. I said quite often mathematicians would just not pay attention to this constant, but we want actually to pay attention to this. And the potential, as we'll see, will have lots of singularities, or some finite number of singularities, which describe wells and walls, different kinds of behavior. So what kind of potentials we're interested in? So we usually have two parts here. One is describes the environment influence on the system, and also interaction. So we usually will have relatively simple interactions here, but with singularities. So I wrote several examples here, including Lennard-Jones potential. So you can see the singularities here, right? And also here. So B and A parameters here. B is so these are numbers here. So why I have this red dots here? Because these are the cases that were not covered in the mathematical literature before we had our results. So as you can see, these are polynomials or singularities of this type. And so it's difficult to apply classical results in this case, but the literature on this subject is huge. So I mentioned only some of this. So, and I just kind of grouped them by different techniques. So Lyapunov function, the techniques that we actually used, also hypercoercivity goes back to Villani, and I will not be able to mention the results of this, the details of this, but so the literature is huge, but the point here is that you can use this to see that you should hope for this geometric or exponential convergence to the equilibrium if you have some function inequality like log-Sobolev inequality, for example, or Poincare inequality. People also used probabilistic techniques such as coupling techniques and other infinite dimensional techniques like distributivity, and so Martin Grothaus, for example, is one of the authors who has a number of publications on these methods. So what we did, and I'll go quickly over this because I know that I should be wrapping up my talk, is that we use these gamma techniques that I mentioned in the beginning, so I want to bring it back here to kind of guess the norm that we should take. So here is this modified Sobolev type norm. So you see that it looks like Sobolev norm, except that there are some parameters here. So you can see that we're still carrying all inverse temperature, friction constant, everything is there because we want to keep track of this in the rate of convergence. And the theorem that we proved initially, and I will not mention some more recent results that we had in even now, is exactly what I mentioned before, is that you have this geometric convergence, meaning that you have this contraction here, right, where sigma is constant that depends on all these parameters you have in the system, that is on the potential. You give me concrete potential like Lennard-Jones potential and the constants that we had in the beginning. I mean, you can write this sigma explicitly for those cases. So you can write not just the geometric convergence to the equilibrium in this case. So remember that we have centered condition here. That's why you don't see this in the inequality. But also, you know exactly how this rate depends on the parameters of the system. So I'll finish with mentioning some of the references that's far from being complete. And it's really about showing you that the subject had lots of different directions, including more geometric properties here, and also some very interesting infinite dimensional results that actually have new approaches now, just this year, and lots of, so Fenyu Wang, for example, has lots of results on how these geometric type conditions can be used to prove a bunch of different kinds of functional inequalities. And also, as I mentioned, some applications, including in probability and in infinite dimensions, and in path spaces with degenerate geometry, but also in, as I mentioned now, is in this Langevin dynamics and how this, so this is a new application of this geometric method, so gamma calculus, as we call it. Thank you very much. Thank you for listening.
Okay, thank you so much for your very nice talk. For questions, please raise your virtual hand. The technical support will activate your microphone, or you can write on the chat also. So let me check. Okay,
Martin.
Professor Martin, let me.
Hello, Martin.
Okay.
Hi, Masha. Nice to see you.
Yep.
Thanks
The
for your
same.
nice talk. I enjoyed.
Thank you.
I have a question to your Heisenberg Brownian motion. What's the invariant measure for that process? Do you know it?
Yeah, but okay, so you mean for the Brownian motion?
Yeah, yes, for the yes, right, for the Heisenberg
Yeah,
Brownian
it's
motion.
a curve measure, which is the same as Lebesgue measure in this case.
Okay, so that means that the generator is symmetric, has no antisymmetric part.
Yeah.
Okay, that's interesting.
So
because
on Karnaugh groups, so the so Heisenberg group with this sub-Riemannian setting, is one of the examples of what's called Karnaugh groups. And the generator for Brownian motion there, or this hyperelliptic, so sum of squares operators, is essentially self-adjoint.
Yeah. Now that's interesting for me, because when I was then not elliptic, in hyperelliptic situations, I always had some more symmetric operator, antisymmetric, and then you had a non-sectorial condition, but that's not the case. You are degenerate, you have just second derivative in two components, but nevertheless it's symmetric and you have hyperellipticity.
Yeah, but it's because it's so the initial example that Hermander had in his paper was actually closer to our favorite Langevin dynamics, which is Kolmogorov diffusion, right? Which is Brownian motion and integrated Brownian motion in this second. But actually, the next simplest example is Heisenberg, but there it's actually self-adjoint, yeah. Essentially self-adjoint, I should say.
Okay.
Why?
Thank you.
Because you have a Dirichlet form.
Yes. And then you have a symmetric
in
Dirichlet
that case,
form.
in Karnaugh groups, you have a nice Dirichlet form.
Yeah.
I didn't talk about it, but all these groups have nice metric structure. So you can, we have a recent paper on that with my former student.
We recently always were studying a situation where you have a generalized Dirichlet form, where you have an antisymmetric part, which is not dominated by the symmetric part. And then we did this hypercoercivity stuff. And I somehow wanted to relate it, but it's not because it's completely symmetric. So
but if you go away from that, so for example, if you, let me give you an example. So if you take any unimodular group, which Karnaugh groups or nilpotent groups are included, or compact type groups included. So you take, say, 2x2 matrices, so-called affine group, where you have translations and rotations, right? Or some positive blah, blah, blah thing. So this is non-unimodular group anymore. So which means that if you take, so left to right, so if you have a right invariant Howard measure and do the right translation, it's not invariant under this translation. So you get redundant cardinal density. So you have right and left.
Ah, okay.
And this is where you acquire the density. But in this, in the unimodular case, you don't have this. So you see what I mean? Like you can, this is, I think, the source of this. So essentially, if you have V group with sub-Riemannian structure, and it's, say, unimodular, including all these nilpotent groups and compact groups, and
that
then
extends
you're okay.
somehow my picture, because for me there was always some symmetric part, and then you had some non-trivial null space of symmetric part, and then some anti-symmetric part was helping you to get ergodicity. But that's now completely different.
But if you want, we can talk about it separately.
Yeah.
You know my WhatsApp, right?
Yeah. Thanks.
Thank you. Thanks for the question. Yeah.
Yeah, thanks so much, Professor Martin, for your question. Okay, does anyone have any question or comment? Anyone? Please.
Okay, thank you very much, Professor Gordina, for your very nice talk. I have a question, maybe a little bit related with the question that Professor Martin did, and also with your answer, right? Because then you mentioned Heisenberg type groups, and so on. But my question is, how much beyond one can go, let's say, for non-unimodular structure? Let's say if one consider non-compact symmetric spaces and also sub-Laplacian associated to some character there, right? Is it possible also to consider you?
Okay, so the question is, what do you want to prove, right?
Right.
So for SL2R, you can actually study the heat kernel in a different way. So non-compact groups would have semi-simple non-compact. I'm sorry for all this jargon, but SL2R is one of the examples where you would have Iwasawa decomposition, and you can use that, but you wouldn't be able to. So for SL2R, they also had this generalized curvature dimension inequality. If you go to higher step-like thing, like in terms, so it's not a kernel group, but you still have like more steps, things become much more difficult. I don't think this technique would give you so much, if that's the question. But I think you might be able to use something else. But it's again, it's you don't have one tool to work with this, okay, anymore. But for SL2R, you can, and I think some other tools should be used actually. Right? It's what I think. So this curvature dimension inequality, I think Feng Yu Wang had paper on higher step type things, but it becomes extremely technical and cumbersome, and I don't think it produces as nice results because generalized curvature dimension does not give you the same kind of functional inequalities you had for the usual curvature dimension inequality. It gives you this reverse type of inequalities, and you can use it for some other applications like this quasi-invariance, but in general, it doesn't give you as good analytic consequences as you would have for the usual Riemannian case. I hope I answered your question, but yeah. So
right, that answer pretty.
So more or less, once you need more than to go to more steps to generate the vector space, right? More than two step, or is it rank of the sub-Riemannian manifold? Things become very complicated.
Okay. And maybe, sorry, maybe it's a good opportunity for me to ask you the following. If you want, maybe look at groups that are more close to, let's say, Heisenberg group, like graded groups, right? And instead of sub-Laplacian,
kernel groups kernel groups will consider it actually, yeah.
Okay.
But you don't use these techniques, geometric techniques there. We use Dirichlet forms for something else. But yeah, if you're interested, again, I can give you some maybe outside of, please write to me and
Okay, thank you very much to Professor Martin for the question and to you also for this illuminating.
Yeah.
Okay, thank you. Thank you. Okay, Andrea. Okay, you can
Hello, Professor.
Hello.
Thank you for your nice talk. I am curious. I don't know if my question makes sense, but I saw some symplectic structure.
Yeah.
Does this symplectic structure influence the invariant measure of these stochastic processes? And how might this affect these constants in these log Sobolev or Poincare inequalities exactly?
So not sure I can. Okay, so the symplectic form is used to introduce new proof structure in this case. So so it's used to so again, I usually think of that as the central extension. So you start with something. So it doesn't really matter that it's finite dimensional. Start with a vector space, you have this symplectic form, you take the central extension. So the invariant measure is for the process or for the semi-group that you consider. So it really depends on the group structure in some sense. So it does influence, but I'm not sure you can necessarily see it explicitly there. The Cauchy dimension equality, so the original proof for its invariance in the infinite dimensional Heisenberg group we did with Fabrice Boudin and Ty Melcher actually used the norm of the symplectic form. So it really appears there, but it's not. So it's more for the analytic results, I would say, but not for the invariance of the measure so much. Also, in the infinite dimensional case, of course, it's more complicated because you don't have a reference Lebesgue measure anymore. So
yeah, because this symplectic measure, which is this Liouville measure, is not invariant, so you have to go to the certain kind of the Riemannian part to make it invariant. So it was my question, like if we can see these constants or if we can see some relationship between these, because sometimes when we work in geometry and this type of inequalities in the constants, you have this information of the manifold. And then I don't know, I am curious that if in the symplectic part you can also see this in but yeah.
So I don't want to flip through the slides, but so even in the beginning and then later when I talked about our results with Bruce Driver, we had the inequality where there was this kappa, which is the curvature. Yeah. But actually, instead of that, you have the different norms of the symplectic form.
Yeah. Okay. Oh, that's nice.
Very explicitly. That's what we did, at least initially. Then there was a different proof by Bruce Driver, Ty Melcher, and Nate Eldridge. They used completely different methods. But again, this proof didn't go beyond step 2. So you can think about it as not a Heisenberg group, but H-type group in infinite dimensions, possibly with multidimensional center, but there are some problems. So there is, I should mention, there is recent work by Ty Melcher and her PhD student, escapes. So, and where they got rid of the finite dimensional center, they can do any dimensions. So and they use slightly somewhat different techniques. Yeah, I should have mentioned that. Yeah.
Thank you very much.
Thank you. Thank you for the question.
Okay, thank you. Thank you, Andrea. Does anyone have more questions or comments? Okay. If not, I have a question. In your settings, maybe it's possible also to investigate the sharpness of the constants for your functional inequalities, for the Poincare inequality or others?
Yeah, so this is what we actually did for the Langevin dynamics, which is kind of technically probably even more complicated, because we really need to. So the method, at least for that paper that I mentioned, we have different ones now. But for that, what we did, we took some compact set in this large space, and we proved Poincare inequality there. And we needed the constants there that depends on this. So it really depends on all the parameters. And if I'm answering your question, if I understood your question correctly. And on the outside of that compact set, we actually use Lyapunov function technique. And we also wanted to keep track of constants because, so the reason why people are interested in how things behave depend on this parameters also on the dimension is because this is used in MCMC and Markov chain Monte Carlo, and people actually want to know the speed at which things converge to the equilibrium. I think the dependence was not optimal, but it's still, we can keep track of it, at least, if I'm answering. So sometimes you can. So for the Heisenberg, infinite dimensional Heisenberg group, the original paper with Fabrice Boudon and Ty Melcher, the constants were explicit also in terms of the symplectic form. So sometimes you can do it. Sometimes, yeah, it's more difficult, but yeah.
Nice, interesting. Okay, so thank you so much.
Thank you all.
Thank you very much, the Professor Masha Gordina, for your very nice talk. Okay, let me check the time. So now we will continue with the break time. So we will return for the poster session 6 p.m. in the Central European time. So thank you very much and see you soon.
Sorry, we have the talk at
yeah, Luc Roncal, 5 p.m.
Yes, 5 p.m. and then
thank you.
Okay.
Yeah. My mistake.
See you at 5
p.m.
See
Central European time. See you.
See you.
There were so many difficulties and hurdles that the Department of Mathematics, IIT Bombay, is one of the largest mathematics departments in the country, and we have the vision of being the best department. I am the first woman HOD of this department. Right from the beginning, there were so many difficulties and hurdles that I could never plan my career. All I knew that I wanted to be a teacher. I was very passionate about teaching. My supervisor, Professor Bhattacharya, who trained me in the area of finite element methods. I was his first female student. He was more nervous, probably than me trying to start with a PhD degree. He was a strict person, but he had a lot of respect and he appreciated my problems. After 7 months of my joining PhD program, I mentioned that I wanted to get married. A couple of years later, I told him that I'm going to have a baby. Then in between, my mother was diagnosed with a terminal illness and my father died. But I believe that the challenges made me a much stronger person. I got a wonderful set of colleagues who really helped me out in all difficulties and helped me share my responsibilities. There are a lot of international projects and national projects which the supervisor and the student can get into. Trying to identify people who are working in the same research area really helps both me and my research students in understanding the current problems and also the new techniques.
She always welcomes new ideas and she always gives us the freedom to express our views, be it in our research or hostel affairs or academic affairs. She is always there for us. She motivates us in every sense.
She comes at very early in the department. I am sure that she will having 100 meetings around. In spite of all those things, she finds time to chat with us and she's really caring.
Her being the head of the Department of Mathematics, there's a lot of pressure on her, there's a lot of work she does. I've not met too many people who work so hard in their life, not just the work aspect but the family and home aspect as well. That's what I love most about my mother.
Excellence in Teaching Awards of IIT Bombay has been constituted to recognize the efforts of teachers, and it's based on student evaluation. I have received this award 3 times in my career. The International Math Union, IMU, is doing a great job in helping women network, and I find this is a very good program in encouraging students and building a confidence in them. For women who want to really excel in mathematics, you may find difficulties, you may find problems, so never give up on whatever you want to do and do good research.
Donc, je suis la 6e dans une famille de 7 enfants. J'aime les mathématiques parce que, d'abord, j'avais eu un modèle, mon grand frère. C'est celui qui est enseignant de mathématiques aussi aux États-Unis. Lui que je voulais atteindre. Je me suis rendu compte que j'étais très bien en mathématiques. Par exemple, laquelle j'ai fait un bac scientifique. Et après mon bac, je me suis inscrite en mathématiques. Il faut être très courageuse quand tu es une fille parce que pour fréquenter même à Yaoundé 1, ce n'était pas évident. Pour avoir une place, il fallait bagarrer pour avoir une place pour faire cours. Donc, et parfois les garçons me demandaient, vous les filles qui font les mathématiques, est-ce que vous allez vous marier un jour? Ils nous décourageaient souvent comme ça. Et ce qui faisait que ça me motivait à leur montrer que moi aussi je peux faire ce que les garçons font. Le titre de ma thèse, c'était la recherche des primitives pour la cryptographie à base de couplage. C'est vraiment axé sur la cryptographie, sur les couplages, qui est une application de l'algèbre. Là où je suis à Marois, je suis la seule mathématicienne de toute l'université. Je suis affectée au département d'informatique et télécommunications. Je suis dans les cours d'algèbre, arithmétique, théorie des nombres. Première année, j'ai près de 350 étudiants. Mais maintenant, quand même, avec le temps, plus le temps passe, il y a plus de filles qui font l'effort d'être là. Elles arrivent à avoir une licence en mathématiques. Peut-être continuer, c'est un peu compliqué. C'est pour ça que j'ai eu l'idée de mettre une association pour qu'on encourage toutes celles qui ont l'idée de faire des mathématiques, pour qu'on ait plus de femmes mathématiciennes au Cameroun. Parce que si une voit déjà une comme moi, ça peut la motiver à faire les mathématiques. Elle dit que si celle-là a pu faire, pourquoi pas moi? C'est venu à part 2015. Quand je suis allée au Kenya, il y avait la rencontre des femmes mathématiciennes africaines. Quand je suis rentrée, j'ai dit il faut que je m'inscrive à cette association. C'est pour ça qu'en 2016, la CAOM a vu le jour. Bon, là maintenant, on peut avoir une vingtaine de membres. Et l'idée que j'aimerais faire de l'association, c'est qu'on la transforme un peu comme un laboratoire. Et chacune a sa spécialité. Moi, je suis en cryptographie, il y a d'autres qui font dans l'épidémiologie et ainsi de suite. Et là, maintenant, dans ces différents domaines, on va faire des connexions et ça va étendre notre association. C'est même l'un des objectifs de notre association, c'est de promouvoir les jeunes filles, les encourager à faire des mathématiques. C'est pour exemple pour laquelle nous commençons à partir du secondaire, on va chercher les enfants au lycée, on leur montre les bienfaits des mathématiques, on encourage à ce que quand ils ont le bac, elles vont choisir les mathématiques d'abord comme filière. Et quand elles sont à l'université, on les encourage à avoir une licence, on les motive à avoir un master, après on leur dit pourquoi pas un doctorat. On est à la fois maman, travailleuse et chercheuse, c'est pas évident de concilier tout ça. Et parfois, à un moment donné, tu as envie de laisser. Mon mari, c'est mon premier soutien parce que sans lui, je n'avais pas eu la thèse. Et même quand je suis à Marois, c'est lui qui s'occupe de ses enfants. Il travaille aussi. Il est enseignant. Il a aussi eu un doctorat en philosophie il y a 2 ans. Et oui, quand je suis à Marois, mes enfants me manquent beaucoup. Ils me manquent terriblement. Pour ne pas laisser, moi, ce qui me motive à ne pas laisser, je pense aux petites soeurs qui viennent, je les dis. Mon souhait pour le futur, c'est qu'il y ait plus de filles mathématiciennes. Parce que je me dis que la femme, c'est la mère de la société. Si vous la motivez, elle va faire mieux. Parce qu'une femme veut, elle peut, quand elle le veut d'abord. Et maintenant, quand elle le veut, il faut mettre les moyens pour l'aider à arriver là où elle veut arriver.
I come from a family with many strong women. My mother was an engineer, so I grew up always seeing her making computations. Iago loves nature. He likes playing with analytic toys, like toys that have some challenge, and I think I also encourage him to play with those, because they were also very part of my childhood. My partner is very supportive of my career. Sometimes have to travel by myself, and I feel safe that Iago is well taken care of by his father. My name is Carolina Araújo. I am a mathematician. I did my undergraduate in Brazil, and then I went to Princeton University to do my PhD. I thought that it was a very competitive environment, which I was not used to, and which did not really talk to my heart. I think that my best memories were in my last year of PhD, when we had a little group of women in mathematics. We used to meet for breakfast, sometimes we would go biking in the woods together, and having that support was very important for me. I work at IMPA, Institute for Pure and Applied Mathematics. I work with algebraic geometry. So I study geometric objects that are defined by algebraic equations. What I've been trying to do is to understand certain geometric spaces by looking at the behavior of curves on this space. My biggest achievement is to be a full researcher at IMPA, and also I have been invited to be a speaker at the International Congress of Mathematicians in 2018. In Brazil, 25% of researchers in mathematics are women, but they're much less visible. It's not uncommon to see a conference where all the organizers are men and female speakers are sometimes even less than 10%. At this moment, I am the only female permanent researcher here at IMPA. this low percentage. It's a problem everywhere in the world. We see this unbalance and this gender gap in mathematics. By excluding girls and women from mathematics, we're losing talents, brains that could be contributing to science. And I feel that it is my moral responsibility to help other women to also excel in their mathematical career. I have 2 female postdocs. They're talented women, and I think it's important to give them the opportunity to show their work and to excel in the career. Right now in Brazil, we are witnessing various movements of women in mathematics, where we try to address the situation. So we organize roundtables and panels to bring this to the community. We're organizing the first world meeting for women in mathematics. It's a silent movement that's happening. This will certainly help in the long run to bring more women to mathematics. For the first time in my life, I am where I want to be. Not only I have achieved my scientific career, but also I am at the point where I feel that I can make a difference and I can contribute to the changes that we must make.
My work is in discrete geometry, having very little information and then being able to tell from that very little information what's the object you're ending up with. That's the sort of problems that I really like working with.
Lately, I am working with applications of algebraic geometry to the study of biochemical reaction networks, how the enzyme cascades, how the signaling pathway act in our cells, in our body.
Functional differential equations are very useful to describe some phenomena that do not occur instantaneously.
I work with probability that involves modeling of stochastic events, which means chance.
I work in reaction diffusion equations in mathematical models. You can give meaning to some important concepts in ecology through mathematics.
I work on pseudo-differential operators. I classify traces and determinants on algebras of these operators.
I think a lot of mathematicians talk about math like doing art, and I think that actually what we mean when we say that is that it's a passionate field, it's an exciting field, you have the freedom of thought. It's really fulfilling at a personal level and an intellectual level.
Once you get an answer, you get such a satisfaction. Gives you this impulse, this encouragement to continue and to do it another time.
In mathematics, you can really state something for a fact. Things make sense. I want to find theorems, I want to prove things. It's not just the laws of nature, but it's also the way how we make decisions. Sometimes we do some kind of mathematical reasoning even when we are not conscious of it.
Chance is everywhere. So many important things you cannot predict deterministically. I mean, they are subject to uncertainties, like the weather, like polls, understanding the social environment.
People say mathematics is not for me. This is not true. It's for you because you are human. We have the ability to speak and to do some math. There is a question of how mathematics could explain the world. We are inside the universe. This is why even if we put into words the circuits in our brain, I feel this is what we do when doing math. It's related to everything because we are constructed the same way as the universe.
What happens to women in mathematics is you are challenged constantly because somehow you're different and you do not fit in immediately with the image they have of the mathematician. You are in a gathering where everyone is male except you. It's not only about the codes, it's also about how a man believes that you fit in or not in this world. The most difficult part is like getting comments from professors where the implication was, you do not belong here.
When people look at me, they say, I don't think that you do mathematics. They don't believe me so easily. So I have to do more work in order for them to believe me. Usually, they ask me if I really did some work. They say, are you sure? Maybe someone else did it already, or it is wrong.
When I will give the first class for the students, they usually expect some old man that will come and give the classes. I never was discouraged to be a mathematician, especially because I had some strong women who inspired me a lot. Because of that, I have the strength to continue, and because also I like very much mathematics.
We are losing talents. We are losing points of view.
Mathematics has not been portrayed in a realistic way in the media, in school, everywhere. I think that we need to find a way to make mathematics more appealing, not just to girls, but to everybody, by showing mathematics how it really is. That is a collaborative activity, that it has to do about thinking and not being fast, that it has to do about learning from others, about sharing experiences.
The world belongs to everyone, and being among the top mathematicians in the world with all the community makes you feel a part of something bigger.
I think the main way to motivate and to help is by your example. We just work.
Now, people are starting to recognize the work of female mathematicians, and it is the work of many of them in all the areas of mathematics. Women are very talented, and you have to have the confidence that you know what you are going to talk about. And once you have this confidence, it's easier, because you know it, you just have to explain it.
Mathematics has this beauty of expressing many different phenomena to group them together in one beautiful concept. When women participate in science, the society wins because we can give something as women. We can give a perspective as women. So I think that when women get involved and when minorities get involved in any field, we all win. I think science wins.
We all have a very different experience of what's being a human being and being alive. And so having more inclusive mathematics ultimately is going to make more inclusive academia and more wholesome. And I'm sure that even though mathematics is super abstract, you bring everything in your culture with you to the table. And I think the science we will do is going to be a better science, and it's going to be much better implications for the world.
Donc, je suis la 6e dans une famille de 7 enfants. J'aime les mathématiques parce que, d'abord, j'avais eu un modèle, mon grand frère. C'est celui qui est enseignant de mathématiques aussi aux États-Unis. Celui que je voulais atteindre. Je me suis rendu compte que j'étais très bien en mathématiques, raison pour laquelle j'ai fait un bac scientifique. Et après mon bac, je me suis inscrite en mathématiques. Il faut être très courageuse quand tu es une fille, parce que pour fréquenter même à Yaoundé 1, ce n'était pas évident. Pour avoir une place, il fallait bagarrer pour avoir une place pour faire cours. Donc, et parfois les garçons me demandaient, vous les filles qui font les mathématiques, est-ce que vous allez vous marier un jour? Ils nous décourageaient souvent comme ça. Et ce qui faisait que ça me motivait à leur montrer que moi aussi je peux faire ce que les garçons font. Le titre de ma thèse, c'était la recherche des primitives pour la cryptographie à base de couplage. C'est vraiment axé sur la cryptographie, sur les couplages, qui est une application de l'algèbre. Là où je suis à Marois, je suis la seule mathématicienne de toute l'université. Je suis affectée au département d'informatique et télécommunications. Je suis dans les cours d'algèbre, arithmétique, théorie des nombres. Première année, j'ai près de 350 étudiants. Mais maintenant, quand même, avec le temps, plus le temps passe, il y a plus de filles qui font l'effort d'être là. Elles arrivent à avoir une licence en mathématiques. Peut-être continuer, c'est un peu compliqué. C'est pour ça que j'ai eu l'idée de mettre une association pour qu'on encourage toutes celles qui ont l'idée de faire des mathématiques, pour qu'on ait plus de femmes mathématiciennes au Cameroun. Parce que si une voit déjà une comme moi, ça peut la motiver à faire des mathématiques. Elle dit que si celle-là a pu faire, pourquoi pas moi? C'est venu à part 2015. Quand je suis allée au Kenya, il y avait la rencontre des femmes mathématiciennes africaines. Quand je suis rentrée, j'ai dit il faut que je m'inscrive à cette association. C'est pour ça qu'en 2016, la CAO m'a vu le jour. Bon, là maintenant, on peut avoir une vingtaine de membres. Et l'idée que j'aimerais faire de l'association, c'est qu'on la transforme un peu comme un laboratoire. Et chacune a sa spécialité. Moi, je suis en cryptographie, il y a d'autres qui font dans l'épidémiologie et ainsi de suite. Et là, maintenant, dans ces différents domaines, on va faire des connexions et ça va étendre notre association. C'est même l'un des objectifs de notre association, c'est de promouvoir les jeunes filles, les encourager à faire des mathématiques. C'est pour exemple pour laquelle nous commençons à partir du secondaire, on va chercher les enfants au lycée, on leur montre les bienfaits des mathématiques, on encourage à ce que quand ils ont le bac, elles vont choisir les mathématiques d'abord comme filière. Et quand elles sont à l'université, on les encourage à avoir une licence, on les motive à avoir un master, après on leur dit pourquoi pas un doctorat. On est à la fois maman, travailleuse, chercheuse, c'est pas évident de concilier tout ça. Et parfois, à un moment donné, tu as envie de laisser. Ah, mon mari, c'est mon premier soutien. Parce que sans lui, je n'avais pas eu la thèse. Et même quand je suis à Marois, c'est lui qui s'occupe de ses enfants. Il travaille aussi. Il est enseignant. Il a aussi eu un doctorat en philosophie il y a 2 ans. Et lui, quand je suis à Marois, mes enfants me manquent beaucoup. Ils me manquent terriblement. Pour ne pas laisser, moi, ce qui me motive à ne pas laisser, je pense aux petites soeurs qui viennent, je les dis. Mon souhait pour le futur, c'est qu'il y ait plus de filles mathématiciennes. Parce que je me dis que la femme, c'est la mère de la société. Si vous la motivez, elle va faire mieux. Parce qu'une femme veut, elle peut, quand elle le veut d'abord. Et maintenant, quand elle le veut, il faut mettre les moyens pour l'aider à arriver là où elle veut arriver.
I come from a family with many strong women. My mother was an engineer. So I grew up always seeing her making computations. Iago loves nature. He likes playing with analytic toys, like toys that have some challenge, and I think I also encourage him to play with those because they were also very part of my childhood. My partner is very supportive of my career. Sometimes have to travel by myself, and I feel safe that Iago is well taken care of by his father. My name is Carolina Araújo. I am a mathematician. I did my undergraduate in Brazil, and then I went to Princeton University to do my PhD. I thought that it was a very competitive environment, which I was not used to, and which did not really talk to my heart. I think that my best memories were in my last year of PhD, when we had a little group of women in mathematics. We used to meet for breakfast, sometimes we would go biking in the woods together, and having that support was very important for me. I work at IMPA, Institute for Pure and Applied Mathematics. I work with algebraic geometry. So I study geometric objects that are defined by algebraic equations. What I've been trying to do is to understand certain geometric spaces by looking at the behavior of curves on this space. My biggest achievement is to be a full researcher at IMPA, and also I have been invited to be a speaker at the International Congress of Mathematicians in 2018. In Brazil, 25% of researchers in mathematics are women, but they're much less visible. It's not uncommon to see a conference where all the organizers are men and female speakers are sometimes even less than 10%. At this moment, I am the only female permanent researcher here at IMPA. This low percentage, it's a problem everywhere in the world. We see this unbalance and this gender gap in mathematics. By excluding girls and women from mathematics, we're losing talents, brains that could be contributing to science. And I feel that it is my moral responsibility to help other women to also excel in their mathematical career. I have 2 female postdocs. They're talented women, and I think it's important to give them the opportunity to show their work and to excel in the career. Right now in Brazil, we are witnessing various movements of women in mathematics, where we try to address the situation. So we organize roundtables and panels to bring this to the community. We're organizing the first world meeting for women in mathematics. It's a silent movement that's happening. This will certainly help in the long run to bring more women to mathematics. For the first time in my life, I am where I want to be. Not only I have achieved my scientific career, but also I am at the point where I feel that I can make a difference and I can contribute to the changes that we must make.
My work is in discrete geometry, having very little information and then being able to tell from that very little information what's the object you're ending up with. That's the sort of problems that I really like working with.
Lately, I am working with applications of algebraic geometry to the study of biochemical reaction networks, how the enzyme cascades, how the signaling pathway act in our cells, in our bodies.
Functional differential equations are very useful to describe some phenomena that do not occur instantaneously.
I work with probability that involves modeling of stochastic events, which means chance.
I work in reaction diffusion equations in mathematical models. You can give meaning to some important concepts in ecology through mathematics.
I work on pseudo-differential operators. I classify traces and determinants on algebras of these operators.
I think a lot of mathematicians talk about math like doing art, and I think that actually what we mean when we say that is that it's a passionate field, it's an exciting field, you have the freedom of thought. It's really fulfilling at a personal level and an intellectual level.
Once you get an answer, you get such a satisfaction. Gives you this impulse, this encouragement to continue and to do it another time.
In mathematics, you can really state something for a fact. Things make sense. I want to find theorems, I want to prove things. It's not just the laws of nature, but it's also the way how we make decisions. Sometimes we do some kind of mathematical reasoning even when we are not conscious of it.
Chance is everywhere. So many important things you cannot predict deterministically. I mean, they are subject to uncertainties, like the weather, like polls, understanding the social environment.
People say mathematics is not for me. This is not true. It's for you because you are human. We have the ability to speak and to do some math. There is a question of how mathematics could explain the world. We are inside the universe. This is why even if we put into words the circuits in our brain, I feel this is what we do when doing math. It's related to everything because we are constructed the same way as the universe.
What happens to women in mathematics is you are challenged constantly because somehow you're different and you do not fit in immediately with the image they have of the mathematician. You are in a gathering where everyone is male except you. It's not only about the codes, it's also about how a man believes that you fit in or not in this world. The most difficult part is like getting comments from professors where the implication was you do not belong here.
When people look at me, they say, I don't think that you do mathematics. They don't believe me so easily, so I have to do more work in order for them to believe me. Usually, they ask me if I really did some work. They say, are you sure? Maybe someone else did it already, or it is wrong.
When I will give the first class for the students, they usually expect some old man that will come and give the classes. I never was discouraged to be a mathematician, especially because I had some strong women who inspired me a lot. Because of that, I have the strength to continue, and because also I like very much mathematics.
We are losing talents. We are losing points of view.
mathematics has not been portrayed in a realistic way in the media, in school, everywhere. I think that we need to find a way to make mathematics more appealing, not just to girls, but to everybody, by showing mathematics how it really is. That is a collaborative activity, that it has to do about thinking and not being fast, that it has to do about learning from others, about sharing experiences.
The world belongs to everyone, and being among the top mathematicians in the world with all the community makes you feel a part of something bigger.
I think the main way to motivate and to help is by your example. We just work.
Now, people are starting to recognize the work of female mathematicians, and it is the work of many of them in all the areas of mathematics. Women are very talented, and you have to have the confidence that you know what you are going to talk about. And once you have this confidence, it's easier, because you know it, you just have to explain it.
Mathematics has this beauty of expressing many different phenomena to group them together in one beautiful concept. When women participate in science, the society wins because we can give something as women. We can give a perspective as women. So I think that when women get involved and when minorities get involved in any field, we all win. I think science wins.
We all have a very different experience of what's being a human being and being alive. And so having more inclusive mathematics ultimately is going to make more inclusive academia and more wholesome. And I'm sure that even though mathematics is super abstract, you bring everything in your culture with you to the table. And I think the science we will do is going to be a better science, and it's going to be much better implications for the world.
En el corazón de América Latina, nuestros proyectos trascienden fronteras para construir un futuro de descubrimiento, innovación y transformación. Bienvenidos, nosotros somos ICMAM Latin America, donde las matemáticas abren la puerta hacia un mundo de posibilidades. El estudio profundo de la naturaleza es la fuente más fértil de descubrimientos matemáticos. Los avances matemáticos están intrínsecamente ligados al progreso de la sociedad en todas sus etapas. Las matemáticas sustentan campos tan diversos como la física, la biología, la economía, la tecnología, la arquitectura, entre muchas otras. Es por esto que en ICMAM Latin America nos dedicamos al fomento de su investigación, con el fin de seguir acercando todas sus cualidades a nuestra sociedad. Nuestra iniciativa nació en la Universidad del Valle en Cali, Colombia. En 2020, celebramos la primera edición del evento y gracias a sus extraordinarios resultados se sentaron las bases para la edición 2022, el cual se consolidó con un alto impacto internacional. En la actualidad, América Latina enfrenta desafíos en la obtención de recursos, becas e interacción internacional en investigación científica. A pesar de esto, reconocemos el talento matemático en nuestra región y su valor potencial a nivel global. Por esta razón, desde ICMAM estamos comprometidos a superar las barreras que limitan el acceso a entornos académicos de excelencia y hemos comenzado a convertir estos desafíos en oportunidades, estableciendo espacios de interacción y alianza entre centros de investigación matemática a nivel mundial. Con la colaboración de más de 50 expertos internacionales, destacamos el trabajo de jóvenes estudiantes de posgrado, promoviendo sus investigaciones, los acercamos a congresos y bienales en diferentes países, creamos espacios virtuales para que los investigadores emergentes interactúen con científicos de renombre, como Terence Tao, Simon Donaldson, Tatiana Toro, Carlos Kenning, Charles Pfefferman, Enrique Suazua y Christine Lauter. Además de esto, prestamos especial importancia en visibilizar y destacar las mujeres de nuestra comunidad científica y matemática en nuestras actividades y alianzas. Reconocemos que solo a través de la colaboración, la unión de conocimientos y la diversidad de perspectivas, podemos superar cualquier desafío que se presente en nuestra sociedad y avanzar en el entendimiento de la naturaleza. Creemos firmemente que la igualdad de género y la inclusión son fundamentales para lograr avances significativos en el mundo de la ciencia y la investigación, y estamos comprometidos en promover estos valores. En ICMAM Latin America, te invitamos a unirte a nosotros en esta travesía donde las matemáticas transforman realidades, hacia el descubrimiento, la innovación y la excelencia en la investigación. Juntos podemos construir un mundo que forje un mañana lleno de posibilidades gracias a la matemática y sus aplicaciones. Únete a ICMAM y sé parte de esta inspiradora historia de cambio y progreso.
Okay. 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 There are participants. It's a pity that we just received a message from Professor Luz Roncal, who is our next speaker, that she cannot connect at 5 o'clock, that she will be here at 5:20 p.m. So in Central European time. So maybe we should wait a little bit for the talk of Professor Roncal. This is an special speaker circumstance, of course. So sorry for the delay. Para las personas que están conectados de América Latina, bueno, es con pesar que nos va a comunicar que la profesora Luz Roncal, que es nuestra siguiente speaker, se conectará unos minutos tarde. Entonces tenemos un pequeño retraso de la programación de 20 minutos. Iniciará alrededor de las 5:20 la charla de la profesora Roncal. Es una situación especial, les pedimos disculpas. On the meantime, maybe we can use this time to know you, to see who are our attendees, who are our the audience that we have with us. So we invite you to open your camera and maybe to interact with the organizers.
Okay, let me check if maybe I have friends here.
Maybe I am not sure if people is able to unmute themselves, right?
Ah, yes, maybe.
Blanca, okay, you can unmute yourself, right? Okay, so everyone can unmute and everyone can open the video, right? Okay. So, okay, Blanca, where are you from? Where are you from?
Hi, good morning or good evening and good afternoon, everyone. I'm from, well, originally I'm from Mexico, but now I'm grad student in Baylor University in Texas, US. So I'm gonna present more what I do in a poster later.
Welcome.
Thank
And thank you for participating in our poster session. It's really nice.
Okay. Para otras personas que de pronto nos sigan de América Latina, en este momento, si lo desean, mientras esperamos la speaker, pueden activar su cámara y desactivar activar su micrófono para conversar con los organizadores. Y con Blanca, que también va a hacer una presentación respecto a uno de los pósters que... Okay.
Blanca, te pregunto, tú eres estudiante de doctorado.
Sí.
¿De qué año? ¿De primero a quinto?
De quinto.
Ah, ya, ok. Ya doctora casi.
¿Ya es doctora?
Sí. Sí, sí.
Depende.
Burocracia.
Sí, sí.
Una curiosidad. ¿Cómo te diste cuenta del evento? ¿Cómo te llegó a ti la información? Porque es importante para nosotros también tal vez saber para divulgar nuestros próximos eventos. De esta vez, ¿tú cómo te diste cuenta? ¿Lo viste por Facebook, Instagram?
Sinceramente, no sé desde cuándo ya sigo al ICMAM, porque yo estuve desde como el primer evento grande que hicieron en el 2022 de matemáticas en Latinoamérica, y desde ahí pues en redes sociales, Facebook, pero, o sea, más bien como, no me acuerdo desde cómo me enteré, pero seguramente pues como soy de México y estudié mi licenciatura allá en México, entonces como que siento que por la comunidad latina.
Ok, ok. Tal vez conoces a Yuriko Pitón, es una de nuestras chefs del evento.
Sí, sí la
¿Sí?
conozco. Ujú.
Ok, es muy bonito ver estas redes, ¿no? Cómo se van ampliando cada vez más nuestro círculo. Bueno, qué chévere saberlo.
¿En qué universidad estudiaste en México?
Mi pregrado fue en la Universidad de Colima, que es un estado muy pequeño en México, y tomé unas clases de maestría en la UNAM, en Ciudad de México.
Ok. No sé si estaría también un buen momento, Duan, para tal vez presentarnos cada uno un poco brevemente también, y ahí le damos el chance y animamos a nuestro público para hablar y ir quitando la barrera de la timidez. ¿Qué te parece?
Por supuesto, por supuesto. Por ejemplo, inicia Karina presentándose, que ha sido la
Ok.
persona de la idea.
Yo que lo propuse. Ok, está bien. Bueno, pues mi nombre es Karina Navarro González. Yo soy de Colombia. Hice mi pregrado en la Universidad del Valle, en Cali, Cali, Colombia. De ahí hice una maestría en la Universidad Federal de Viçosa, eso ya es Brasil, en el estado de Minas Gerais. Y luego de esto comencé mis estudios de doctorado en la Universidad de San Pablo, en Brasil también, en el estado de San Pablo. Actualmente, bueno, después, eso lo terminé el año pasado, defendí el 24 de octubre del año pasado. En noviembre, el 2 de noviembre, me fui para Armenia, que es un país muy pequeñito, no la ciudad, tenemos una ciudad en Colombia también que se llama Armenia, pero no es la ciudad. Hay un país que es pequeño que queda en Asia, que se llama Armenia también. Y de hecho descubrí que se llama Armenia, aquí me voy a extender ya con las historias, pero descubrí que se llama Armenia por causa, la ciudad en Colombia se llama Armenia, por causa del genocidio que tuvo este país unos años atrás. Entonces muchos armenios se trasladaron a algunos países de Latinoamérica, entre ellos Colombia, y en homenaje a estas personas muertas, ¿no? Fallecidas, se creó una ciudad que se llama Armenia, como el país. Eso ya fue hace mucho tiempo. Bueno, ahí me fui a hacer un postdoctorado, estuve un año y ahorita estoy en Israel haciendo mi segundo postdoctorado en el Instituto Weizmann, en la ciudad de Rehovot. Y hasta ahora vamos por ahí, en ese paso. Esa es mi pequeña y breve historia. ¿Quieres seguir tú, Duan? Ok, nuestra profesora Luz Roncal llegó.
Sí.
Hola, perdón por el retraso.
¿Cómo
No,
estás,
tranquila.
profesora?
Bien, bien, ya lo siento, ya lo siento.
Sí, no. Queríamos antes proponerte, resulta que le hemos anunciado a nuestros atendís que vamos a iniciar a las 5:20. Que vamos a iniciar a las
correcto.
5:20. ¿Tú crees que podamos esperar 10 minutos más de pronto? Porque algunos salieron.
Por
Esperar.
supuesto. Sí, por supuesto, sí, no hay problema. Gracias, hombre, claro que sí. Sí.
Claro. No, aquí, por ejemplo, los organizadores, Karina eh, le surgió la idea de presentarnos para conocernos un poco más. Entonces, ¿por qué no comenzamos con nuestra speaker? Que nuestra speaker se presente también.
Sí, perfecto.
Sí, de acuerdo. Seguimos en castellano, ¿no? O sea, no hay nadie que sepa que no sea castellano hablante.
No, I think we have.
Ah,
Ok.
Yeah,
okay,
maybe it's
okay.
better to change to English again.
Okay, great. Okay, so yeah, well, hello everyone.
Hello, everyone.
Yeah, I'm
Hello.
I am Luz Roncal. I am a researcher in Bilbao in the Basque Center for Applied Mathematics. So, well, this is a research center in the Basque Country. It's in the north of Spain. It's not connected with a university, although we have a lot of scientific bonds. And well, before that, I go to a PhD here in Spain as well, in the University of La Rioja. And my research interests are essentially harmonic analysis and its applications to PDE. Actually, there are several directions that I like. My background was actually harmonic analysis related to orthonormal systems, but life is very long, and then you meet people, and then you learn things, and you have curiosity. And actually, right now in Bilbao, we have a big group of people with different interests, and it is easy to discuss different topics with different people and so on. And I don't know if this is just enough for an introduction. Thanks for inviting me, and congratulations for this event.
Thank you very much. Thank you very much. Yes, I remember well Bilbao, and Beckham. I went there, yes, a few years ago. Okay, maybe let's say Andrea, maybe Andrea want to present first. Oh, you can see Alexandra there, and also Duvan Alexander saying hello. Oh, crying. Oh.
So, hello everyone. My name is Andrea Hurtado. I am from Colombia, from the same university as Milton, Karina, and Duvan. Gladly. So I did my bachelor there. From there, I moved to France for 4 years. And currently, I am studying my PhD in Germany. It's in an intersection between differential geometry and stochastic analysis, which is called stochastic differential equation. Yeah, it's related to stochastic differential equations with differential geometry, symplectic geometry. So it's with these areas right now. Before I was doing geometric analysis. So I have been always been with this direction of geometry. And yeah, now I got the opportunity a few months ago from Duvan and Karina and Milton and Yuriko to be part of this group, ICMAM, that they created a few years ago. They have been growing a lot, which I am really happy now that I am part of this group. And it will grow more. It will continue with these nice events, you know, having the opportunity to connect with people that we don't have to connect Latin America with the world, because some people, they don't have the opportunity to go outside. And now we can have these close relationships with Latin people, and then professors from these areas, and they can really talk to them, ask them, have this connection. Is really, I'm really proud of being part of this organization right now. And yeah, that's all I have to say. Thank you.
Thank you. Thank you. Very well. So not just in few words, I would like to present myself, but better, I prefer to present ICMAM Latin America. To present ICMAM Latin America. So maybe for Professor Luz Roncal, right? Maybe just let me tell you about our research organization. We start our projects in 2020 in the pandemic time, right? It was a nice opportunity that time to create spaces, right? To share the let's say, experience about mathematics, we create an event from Universidad del Valle in Cali, Colombia, virtually. It was a local conference with local people, Colombian researchers. And then we noticed the powerful of organizing virtual projects, right? Virtual conference, for instance. Then suddenly we start growing every 2 years. We continue organizing the conferences, and with more people joining ICMAM Latin America, and then also our projects starting growing. Actually now then we are a research organization that operates like an international society, right? Of researchers from Latin America. Then we have several projects. For instance, we work for the visibility of the mathematical work of young mathematicians from Latin America, also for the visibility of the work, of course, of women mathematicians. And the main goal is to allow young people, right, from Latin America to interact with researchers around the world, right? So in that way, with our conferences, international conferences, we invite many people, and then we allow this that we are doing now, right? That is that maybe people in Latin America that essentially don't have funding maybe to go to conferences outside can interact with, let's say, speakers, right? Specialists in mathematics like Professor Luz Roncal and other speakers. And maybe that's one part of the work that we do in ICMAM Latin America. Just let me say that we start also, I will mention maybe this later in the closing ceremony, that we start also creating agreement with several international societies like ISAAC, the International Society for Analysis, Applications and Computations, and applying for projects with the International Mathematical Union, right? For our projects. With Springer, publishing the work of young mathematicians and female mathematicians also. Then this is maybe something that I can tell about ICMAM Latin America, ICMAM Latin America, right? And this conference then is a joint work with ICMAM Latin America and ISAAC, the National Society for Analysis, Applications and Computation. So maybe this is a short overview about what we do in ICMAM Latin America in recent times. Okay, so well, maybe it's time to start the talk of Professor Luz Roncal. So thank you very much, Professor Luz Roncal, for accepting our invitation. You can unmute yourself, right?
Yes, yes.
Okay.
I should now try to share my screen, I think.
Okay, let's try.
A ver, let's check this to one. Okay, but I don't. Can you see my PDF?
Yes, we can see well.
Okay, and then I can, if I do a whole screen, can you see it?
It's in full screen mode, yes.
Okay, so perfectly. And wait a second. This is also perfect.
Right, you can move slides, yes. Okay.
Great.
So maybe just let me make a short presentation about Professor Luz Roncal, right? So for our attendees, just let me say, it's my great pleasure to introduce our next speaker, Professor Dr. Luz Roncal, who is a researcher at Iker Basque in the Basque Center for Applied Mathematics, BICAM. In 2020, she obtained a Ramon and Cajal contract, which she also holds at BICAM. Luz Roncal collaborates in research with the mathematics department at the University of the Basque Country. As she mentioned before in her presentation, she earned her PhD from the University of La Rioja, where she worked as an interim associate professor. She has undertaken research stay at the University of Helsinki, the Indian Institute of Science in Bangalore, the Isaac Newton Institute in Cambridge, Oberwolfach also, and the Polish Academy of Science in Wrocław. She's a member of the governing board of the Royal Spanish Mathematical Society. Her research focused on the fields of partial differential equations, analysis, and harmonic analysis, with internationally recognized contribution. She received a Leonardo grant from the BBVA Foundation, aimed at supporting researchers and cultural creators with highly innovative scientific, technological, or cultural outputs. In 2019, she was awarded the Young Female Scientific Talent Prize by the Spanish Academy of Science Foundation and MasterCard. She also won the Oviedo City Scientific Essay Competition on the mathematics of the 2020 Princess of Asturias awardee. So it's really our great pleasure, Professor Luz Roncal, to have you in this conference of Women in Mathematics. Thank you very much for accepting our invitation.
So thank you very much, Duvan. Thank you everyone in the organizing committee, Karina and the others. Thanks for coming and for waiting for me. I had some small technical problem and I was not able to contact before. According to also what you told me, when you wrote to me to ask me about this talk, there was an invitation to explain very briefly why I have this, how can one maintain a curiosity in research every day? What is the motivation for that? And actually, I think that before today, I was talking to some colleagues that are mathematicians as well and colleagues. And in the end, mathematics is also, probably the main part in mathematics in a career is the human relationship, right? So for me, it's a privilege and it's very fun to work with other people from other countries, other cultures, just have fun, struggle with a problem. Sometimes you are alone, but sometimes you have a friend and then you discuss and that sometimes you argue. And this is really motivating. And other people ask questions to you. So all this environment, this social activity around mathematics, I think is one of the most motivating, things to convince you every day that this is fun and we are privileged in some sense. So, yeah. Having said that, I will go to the talk. Okay, I prepared a talk. Since I have 45 minutes. At the beginning, I prepared something a bit long, and actually there is a part that is quite technical in the end, and I think I will not risk this because I think that I thought when I was preparing this that it was good to give a big overview of the topics I'm talking about, right? Because I think that the audience there is a wide variety and probably it's better if we learn something today. So the title is Directional Singular Integrals in Codimension 1, and actually it's a contribution that I've been doing a couple of years ago with my collaborators. Yanis Paris is in Bilbao, but also Odysseas Bakas, that was now is in Greece, was in Bilbao as a postdoc, and Francesco Di Plinio from Italy. So I'm going to start with some very, very elementary blocks in harmonic analysis, which are the Hardy-Littlewood maximal function. Okay, so you take a function, absolute value, you take an average and take the supremum over all radius in this average. So this is central object in harmonic analysis. There is also another notion that is ubiquitous, that is they are the singular integrals and whose prototypical example are Hilbert transform. Okay, so here we are in R, and this is a principal value saying that we are taking a limit when you are approaching to the singularity. This way, y equal when the modulus of y tends to 0. Okay. So let me just look at this object a bit more carefully. You can write, I'm a bit hand waving, but essentially you can write this operator if you look at the Fourier transform in the Fourier side with its frequent, the corresponding multiplier, say, and you can write the Hilbert transform as this operator here. So the symbol is the sine of t. Essentially, you can say that you are looking at the frequencies that are in the half positive line, and then you put 0 when you are in the half negative line. Okay, so this is the multiplier, or this is the operator which corresponds to this multiplier. Okay, so as I mentioned, these are ubiquitous, and then one can start playing with the modifications of these objects. So let's start looking at the following modifications. So let's take a set of directions, okay? Set of points in the sphere, so it means that we are having different directions. Fix one of them, pick one direction, fix a scale, R. And now, if you remember the maximal hard-reducible maximal function, now what I'm going to do here is to run these averages, but now I'm going to move the points here along this certain direction that I picked. Okay? So now instead of having just fx or ft, now I'm putting x minus tv. And I'm taking this average along this direction. And analogously as before, now I can take the supremum over all radius, and this is a directional maximal function. Okay, directional hard-reducible maximal function, if you wish. You can do the same with the singular integrals and with the prototypical example. Let's start doing with this prototypical example of the Hilbert transform, saying that if you remember now, before we had fx plus t, dt over t, but now we are going to put to run the values of the function along this direction v that I picked. Okay, so this is a directional Hilbert transform, and again I can just write the operator in the Fourier side and taking the inverse Fourier transform. So now the symbol, the multiplier, which corresponds to this operator, is the sign of the scalar product chi times v. So yeah, by the one-dimensional theory, actually one can prove that these two operators, because, well, yeah, I probably, one of the things that harmonic analysts are mostly interested in is to know about the regularity properties of operators, in the sense that are they bounded, for instance, in LP? From LP, if you take a function LP, they send function LP into functions in LP. Okay, so we are interested in looking at the LP boundedness of these operators. Okay, and by the one-dimensional theory, actually these two directional operators are uniformly bounded in LP. No, because one can essentially reduce this situation to the previous situation. Okay, so this works fine, and then we can just go a bit further. And okay, recall this is the directional maximal direction along one direction. This is the directional Hilbert transform, and one can start thinking, okay, why do you want to look at these directional versions of the maximal function and Hilbert transform? Well, because in particular, for instance, they have or they arise in the method of rotations developed by Calderon Zygmunt to study singular integrals in Rn in the 50s. Okay, so actually these operators arose naturally when looking at prototypical objects in the theory of harmonic analysis, real harmonic analysis. Okay, so these operators are not the aliens; they are something. And now one can start thinking, okay, what's going on if I take a lot more of directions, or I try to get a collection of direction and I look at them the maximum over all the set of directions that I pick, right? And this is what I'm saying, no? What if now, for instance, let's look at the directional maximal function. I take this arbitrary set of direction, and take the supremum over all directions of such a chosen set. Okay, so now I have this maximal function, M capital V. And if I take here the supremum over all scales, the M capital V. One can do the same. One can think about the analogous version for singular integrals. No, the analogous situation when of the directional Hilbert transform when taking the supremum over all directions, and even more generally, this is what I wrote. You can just write. Remember that the directional Hilbert transform had a symbol that was the sign of T times V. So in general, take a multiplier, something called Hormande multiplier, saying that Well, some function who has certain smoothness property, and then write such an operator, and then take the supremum over all directions on the chosen set. Okay. So now let's do the same question. Are these operators M capital V, T, M capital V bounded in LP? And okay, so just to give a taste before answering the question, and these operators are described in frequency. So looking at the symbols, not looking at the multipliers. And actually, this is just to have an idea, no? That, for instance, if I take an average, no, in one direction, and look at the average, no, this is the average. This would be minus R, etc. Okay, and I look at the Fourier side, and even if I put here a smooth function, I look at the Fourier side. Actually, this operator is looking essentially to a band, okay, of growth 1 over R in this, and this is the direction, okay? This is the perpendicular direction. So essentially in the frequency, in the Fourier side, this is the operator. This is the description of the operator, and it's 0 everyone else. For the directional Hilbert transform, if you look at the Fourier side, remember that in one dimension, just the Hilbert transform, not the directional, so say the direction in the this axis, it was 1 in this direction and 0 in the other. And now we have a multiplier that is the sine of T times V, and this means that this will be 1 in all this upper half plane, and it will be 0 in the other. Okay, this is the frequency description of these operators. And actually, one useful trick to look at if you want to study boundaries of these operators, or even actually the supremum over all directions, is the so-called the method. Well, you linearize the maximal multipliers, and instead of taking the sup over all V in capital V, you just take this V like a measurable vector field, okay, like that, of directions. Okay, this is a way of linearize the operators, and then if you want to look at the mapping properties of these operators, then you have to, well, it's enough to look at this kind of operators. Okay, this is one thing. So I'm just describing the situation, and actually, in order even to a way to study better the operators, that okay, I can truncate the scales and look at the boundedness of these objects, and if these bounds are uniform in epsilon, then I will be okay. Okay, so this is just a way to familiarize that these are typical approaches to look at these operators. Okay, so as I mentioned, so my goal or the goal is then to study LP boundedness of these maximal directional operators. Okay. Either the corresponding analogous to the Hardy-Tuoll maximal, or the corresponding to the singular integral, but taking supremum over a set of certain directions. Okay, so the problem is that these directional objects, or the LP boundaries of these directional objects, sometimes fail to be bounded, and the failure of such a boundedness can be tested or can be found by testing what is called Kakeya counterexamples. Okay, and then I thought that it was a good idea to refresh or to introduce for people who don't know about this, which are Kakeya sets, and then connected to my setting. Okay, so okay, so the goal is this, and I just making in advance, saying in advance that these operators are going to fail to be bounded, and actually this can be proven by using these Kakeya counterexamples. Of course, I will explain later that not everything is lost. If you have an arbitrary set of directions, then probably you will not have LP boundedness. But if you start putting restrictions on this set of direction capital V, then you can get some. Okay. Okay, so just then an aside. What is a Kakeya or Bezikovic set? So this is an aside, independently from what I started with. So let's consider a set of points in Rn, which contains a unit line segment in every direction. So for instance, you have here a circle, so of radius or diameter 1, so this is 1. Or you can have a equilateral rectangle, triangle, or you can have this shape here. And actually, all of them satisfy this blue description. And now I can ask which is the minimum area, or which is the site who has a minimum area. So among these three, this is the one who has minimum area. But among all sets of points with this property, which is the one with minimum area? Okay, so Bezikovic proved that there exist sets of Lebesgue measured 0 in Rn which contain a unit line segment in every direction. And these are called Bezikovic sets, okay? Sets that contain a line in every direction of unit measured unit, and then the whole set has Lebesgue measure 0. And then one can think of, okay, Lebesgue measure 0, can I, among all of them, can I use other kind of dimension, like Minkowski Hausdorff dimension, for instance, to measure and compare if there is a smaller or bigger or whatever? And here is what is called the Kakeya conjecture, okay? Kakeya was a Japanese mathematician, and Kakeya conjecture says that the Bezikovic sets cannot be in any smaller measure-wise. Which quantifying, this means that you cannot find these Bezikovic sets with Hausdorff dimension less than D. Okay, they have to have dimension D. So this conjecture was solved in 2 dimensions by Davis in 71, but this is a big open conjecture that is open for dimension greater or equal than 3, and actually the most recent progress by these people say that, okay, this Bezikovic set has to have at least this dimension 2 minus square root of 2 times D, okay? Actually, as I mentioned, this is one of the main conjectures in analysis and, of course, in harmonic analysis. Okay, so an example of construction of Bezikovic set is given what is called the Perron's construction of sprouting triangles. And actually, so you start with a triangle like that, you split in the middle, then you move this part towards or the left part towards the right, and then you can do the same by splitting in many pieces, and then you move and group 2, 2, and then you put them together, 2 and 2, and then you repeat. And well, so this set will be a Bezikovic set, okay? 0 Lebesgue measure, but with 1 unit segment in every direction. And you can do this because then you can dualize this situation and put it just upside down, and that's why you find all the directions. Okay, so this is the idea. You can just repeat this idea of sprouting triangles by looking at a triangle that starts just upside down and do the same game. Okay, but now if you look at these triangles a bit carefully, you look at one of these, for instance, this one and the dual. You can put inside a small rectangle, okay, small rectangle here and a small rectangle here. So these 2 rectangles are separated, well separated, say. They cannot be touching itself. And actually, what in this construction, what one can prove is the following. Sorry. What one can prove is the following. So this construction is a quantitative Bezikovic set in this sense. So for every epsilon greater than 0, you can find a collection of 2 to the n rectangles, like the ones that I put here, this R, of side length 1, that is, this is 1, but the short length very, very small, like 2 to the minus n, and such that if I take the union of all of them, remember that here there are more triangles and they will be overlapping, the union of all of them, the measure of the union of all of them is very small, like epsilon. But if I take the collection of these translated rectangles, which are disjoint, so this means that there exists a pair with disjoint rectangles such that each rectangle is a translate of one of these in the direction of the long side, and the union, the measure of the union of all of them, these are disjoint, this is summing all of them, is the O of 1, okay, it's a constant. So the union of all of them, of the original ones, is very small, but if I translate them, they have a big measure, okay? So, okay, this is just repeating the same, no? This comes from this construction of exploding triangles, and these are coming from translating these rectangles inside the triangles. Very good. So this is a Kakeya or Besicovitch set, and this is just repeating the same, but with a different way of saying is that, because now I'm going to connect with I said at the beginning that we are having our maximal operators. We are interested in the LP boundedness, but what I said is that unfortunately, if we take an arbitrary set of directions capital V, what will happen is that not always these operators will be bounded, and actually the counterexamples will come when testing the operators on Kakeya sets. Okay? And this is what I say. No, if I take, for instance, in R2, a family of, I will call them now tubes. Okay? Remember, these are the tubes that overlap from this sprouting triangle procedure, and I take the translates, and then I can choose the directions of the tubes given by a set of directions given V delta, right? No, I choose a capital V delta, say delta, let's put this net. So I have a sphere, and I put points which are separated by delta, and then I take all the directions pointing to these directions. So each of these will be a pink tube overlapping, but then I can translate them, and this will be a situation of Kakeya type, okay? So the union of the translates, which are these joints, will have measure B, are these joints, but the union of the pink tubes will be, this can be proven, will be of measure very, very small. So, okay, delta is a small number. Okay, so this has been, of course, studied and proven by several people. I have several names here. And the thing is that, this is moved. This should be matching these points. What happened is that when I take my directional Hilbert transform and my maximal directional operator tested on these tubes given by this direction given by this delta net, so the operator norm is bigger than that, and this blows up wherever P is greater or equal than 2. Okay, in this case, for this fails, and there is no hope to choose this arbitrary set V delta to have LP boundedness for these operators. Okay, so not everything is lost, as I mentioned. So, for instance, Kakeya type counterexamples make my operators fail to be bounded, but there is hope to choose other sets to have boundedness of the operators. For instance, if I take a set of directions, I put which are finite order lacunary. Well, just the thing that you have like a sector. Look, think of the circle, and then start putting a direction to the 1/2, and another in 1/2, 2 to the 2, and another in 1 to the 2 to the 3, and so on. So lacunary. Make a lacunary splitting of the sphere, and then put a direction in each of these points. Finite order lacunary means that you can, in each of the arcs, you can start doing another lacunary decomposition and so on, but essentially this is the idea. So when you take a directional maximal operator tested in this, or defined, sorry, in this set of directions, then this operator will be, can be proven that it will be bounded from LP into LP for P greater than 1. Okay? So, well, there is some literature and higher dimensions and this and that. There is, by the way, there is an interesting reverse question that is natural. So, for Kakeya, I have counterexample, I don't have boundedness. For the finite order lacunary, I have boundedness. Just the converse, is the converse true? If I have a directional maximal operator bounded from LP, this implies that the V is lacunary, and well, there are interesting results in that direction, something actually very, very recent that, well, is essentially it's not clear that this question is closed yet. Okay, so okay, one can also look at the directional Hilbert transform, and directional Hilbert transform fails to be bounded when you choose the set of directions B to be Kakeya, but actually directional Hilbert transform has also non-Kakeya counterexamples, so you can find other kind of set of directions for which the boundedness fails. Okay. And okay, so this is a bit the situation, right? So, so what is the point? I just presented these directional operators. I said that for certain sets of direction this is working, for others not. And now let's look at the way, as I mentioned before, that let's look at these operators in its linearized version, okay? Which is another way to look at the problem. Okay, so let's write our operators in linearized form and truncated form in this way. So here V is a measurable vector field. And then one can make the same question. What do I have, the reformulation of which kind of set of direction can I choose? I can put the question saying that, how do I have to, or what do I have to impose on this vector field to make my operators to be bounded? Okay? So Antoni Sigmund and Elias Stein, that are, you know, say, fathers of real harmonic analysis in the 20th century, suggested that you can have boundedness. It means that you can avoid Kakeya counterexamples if you impose smoothness assumptions on this vector field. Okay, so let's look at this as a function, as a vector field, and what do I have to ask to this vector field to have my linearized version bounded? So if I ask V to be Helder continuous with alpha less than 1, this doesn't work. Okay, one can still find Kakeya counterexamples. So this is not working. So for the case of the maximal function, actually Sigmund was the one looking at maximal function in this form. Sigmund suggested that if you ask the vector field to be Lipschitz, and with the scale quantified by this Lipschitz norm of the vector field, then if this happens, then the operator should be weak type weak type 2-2. Okay, and Stein later conjectured that the same would happen for the directional Hilbert transform. Okay, so these are called Sigmund and Stein conjectures. Okay. This is what I said, just one by one. So if I look at the truncated directional maximal transform linearized, dimension 2, Sigmund's conjectures say that if V is Lipschitz, then for suitable epsilon greater than 0, this operator is of weak type 2-2. Good. And this is the second. What I mentioned is that Stein's conjecture says that if V is Lipschitz, then truncated directional transform along the V is of weak type 2-2. Okay. And remember that if V is Holder continuous for any index strictly less than 1, these results are false and the counterexamples are Besicovitch sets. Okay, so more in this direction, for instance, it is known that if the vector field is real analytic, then these operators are bounded. First shown by Bourgain, later contribution by Stein Street, Guo. And actually, the point with Bourgain's argument in this case is that you can decompose your vector field in a C1 plus epsilon part, and then you have to look at some geometric condition saying that, well, it's saying that no integral curve of the vector field is a straight line, something like that. Nevertheless, again, people try to look at these operators in different ways or imposing some restrictions and see if something can be done. And in 2006, and this is an important contribution, Lacey and Lee, what they did is to look at the linearized version of the directional Hilbert transform. And then they look at some, in the Fourier side, they restricted the action of the operator to a single band. So to functions that are supported in a single frequency band. Okay, so what's happening if I just take these kind of functions? So what happens is that they prove actually that the operator, this operator then, this was of weak type 2, and bounding LP for p greater than 2. Okay, and here they only ask V to be measurable, a measurable vector field. Okay, so when you restrict the action of this operator to functions who are supported in frequency in a single band, like frequency 1, say, and then you can admit that with just measurable vector field, this operator will be bound. Okay, this is interesting because it opens a new way to look at the operator, like restricted to these functions. And actually, this is because one can say, oh, but this is very, very restrictive, just looking at functions who are frequency projected in one single annulus or a single band. But it happens that actually from this single annulus vector field problem that Lacey and Lee proved, one can deduce, if you have Lacey and Lee, actually Lacey and Lee say that, one can deduce the so-called Carlson theorem on point-wise convergence of Fourier series. And this is one of the major problems in harmonic analysis ever, right? And it's a hard problem. So actually, what it's saying is that first that the result of Lacey and Lee is really strong, and actually that the conjectures that we are looking at are very, very difficult. Because, just with this restriction, you are having something very, very strong. Of course, there are other open questions like vector value. What about vector value versions of Lacey Lee? And this room to work. Okay, so there are other contributions in the direction of Lacey and Lee. Always, these are contributions in 2 dimensions. And also, looking at, for instance, when you have vector fields that depends only in one variable and other stuff. Okay, so some more contributions. And I was not insisting much, but I was all the time looking at this directional Hilbert transform maximal maximal function all the time in dimension 2. The point is that what happens when one looks at higher dimensions and what happens when one looks at the most general situation of singular integrals. And here is where I am just, I think that with the time I have, I will just try to put the context of the problem and state our result, okay? So now we are interested in studying LP boundedness of general directional singular integrals. Means that here you have a general multiplier, maybe with some, you have to impose some, at least some smoothness assumptions, like Hormander-Milling-Hormander, and then you take a set of directions and then take the maximal of all of them, okay? So if I wrote here in dimension 2, but if you write in higher dimensions, you can think that, okay, you can think of a multiplier in which is defined for functions. So here the input is a variable in dimension n-1. Okay, so the kernel has dimension here, the kernel has dimension n-1, and what I'm saying is that, okay, n-d is 1, and this kind of multipliers are co-dimension 1 directional multipliers. Okay, so I can then take, for instance, on all, I can take Grassmannians of dimension d, no, of co-dimension 1 Grassmannians, and then for each of them, I have for each element of the Grassmannian, I have a orthonormal basis. So each of these symbols, I can write them in terms of, for each element of the Grassmannian, I can write the corresponding variable like this, not this product like this. And then now I can take the supremum over all elements of the Grassmannian. Okay, so to give sense to these operators, no, then what I have to look at is these operators here. No, this would be like the co-dimension 1 version of a directional multiplier. Okay. So this is our object, and we would like to have LP boundaries. Of course, this is not something. Well, one has to look for an example, no, at least. And actually, when you take the multiplier to be essentially the symbol of the vector of d-dimensional Riesz transform and put it here, well, this is an example of this multiplier. Also, it may happen that if you take the supremum of all Grassmannians, it may happen that this will not be bounded, and maybe you will have to restrict yourself to a subset of elements of the Grassmannian. No, that in the sense that maybe for all sets of directions, your directional Hilbert transform is not bounded, but if you restrict to something, it will be. Okay, so this is the object. Well, this is the example for the vector of d-dimensional Riesz transform. This is a particular example. And then what we proved is like, let's say, singular integral or multiplier directional version in codimension 1 result of Lacy and Lee. So if we take our operator linearized and we apply it to a function who has frequency support in a band, then we can deduce, and of course we have to impose that our multiplier has some regularity, like log holder. Then we can prove that this operator is founded in LP for p greater than 2 and of with type 2. Okay, this is our main theory. Do I have like 2-3 minutes? Is that okay?
Yes, yeah. Yes. Don't worry. Even more. You want 5 minutes? 5 minutes, 10 minutes?
5, 10. Okay, I will try to not reach 10, but thank you. I will make use.
Okay.
So yeah, in particular, so when you restrict the set of directions to a set. Remember, no, in our case, the directions for us are given like elements of a Grassmannian. So if one restricts the set of the elements of the Grassmannian to a set of cardinality capital N, actually we can prove, no, as a corollary of this, that the operator is bounded from L2 into L2, so you get something better. Without restriction on the functions, and the operator norm is of the form log of n. Okay, this is sharp, and this is saying that you cannot take an arbitrary set of Grassmannians or directions. In our mind, we have this because, of course, this will blow up as long as the number of directions go to infinity. Okay, so. It can be proven as well that once one has this result, no, the same as, well, Lasianly deduce the Carleson theorem. So actually we can from this theorem, something called Carleson's Holin theorem can be implied in the sense that, well, this operator is bounded in LP. This is Carleson type operator. Okay. So, okay, probably because I mentioned, no, this is at some point it starts to be very technical. Let me just explain the idea. Okay, this slide is maybe encoding the whole plan. So first of all, we are dealing with variable multipliers. Okay, so for each element of the Grassmannian, we have a multiplier, and we assume some smoothness on log modulus of continuity. So, well, this is something that it is like that. We need this smoothness in the proofs. And it's somewhat a bit natural, but we cannot remove that. And here the problem, and actually this is something that when one starts looking at the operator and starts attacking the problem, then one realizes that well, the Grassmannians, actually, one can think of elements of the Grassmannian, one can think of rotations from the one Grassmannian to the hyperplane RD. So each Grassmannian can be thought like that. So to look at the operator we are interested in the end is to look at an operator in which you have elements of the Grassmannian and rotations to elements of the Grassmannian to RD. So and then we take this supremum. And if one when looking at the operator, one understands that if you take this maximum here, this supremum here, that means that you have rotation invariance. The problem introduces artificial discontinuity. So the operator starts to get a lot of discontinuities, and this is very difficult to graph them. Okay. So the first technical difficulty is try to remove this maximality, and well, and this can be done, of course. But this is what I want to say. This is an additional difficulty when you are in a higher dimensional setting, or this higher dimensional setting of the Grassmannians. When you are in 2 dimensions, you don't see this rotation invariance because you are just taking you are not rotating to some you are not identifying a Grassmannian with an hyperplane. You don't have to make this rotation. Okay, yeah, this is what I was saying, that essentially in dimension 2 there is just one unique rotation from R to the corresponding direction. When you are in a higher dimension, you can rotate like this, you can rotate like the other or the other way, and that's. So this is one of the main difficulties, or one additional difficulty. And the second is that, okay, good, we remove this rotational invariance, we end up with this operator. How to deal with this operator, okay? So the way to analyze the operator is to discretize the operator using something called time frequency analysis. Okay, so I will not have time to explain much, but the point is that time frequency analysis tries to decompose an object in general, looking at the real part, the space-time, and the part in frequency, no? After looking at the Fourier transform. So you try to localize as much as possible, both in time or space and in frequency. Okay, so just trying to split the operator and trying to put a function on each of the pieces such that you get most of the information, and both in space and in frequency. Of course, it's impossible to localize simultaneously both time frequency because of the uncertainty principle, but this is the idea, okay? So discretization of the operator looking at frequency, time and frequency, but the point is that this is a so far well-known technique in 1 and 2, even 2 dimensions, but not in higher dimension. And one has to, well, to work out this directional nature of the operator to construct a good, what is called a model sum, discretization of the operator, in terms of these pieces that are called wave packets. And they have to be very much attached to the geometry. And then you have to localize in this higher dimensional, and you have to look at how are these frequency caps. Yeah, probably I will not talk much. Well, I just explain a bit how to remove this rotational invariance that I will just skip. This what I say, no, that one is able to remove this rotational invariance by looking at one specific rotation that is smooth, that is canonical. So you are reduced to prove something that removes this supremum. So in the end, our problem reduced to look at some operator which takes the supremum over elements of a Grassmannian of an arbitrary set of Grassmannians, and here I'm just this is, I think I will just stop here, no, and this is actually the theorem that we prove, no, that this operator with a rotational invariance applied to a frequency projection band, single band, maps L2 into L2 infinity and LP to LP, uniformly over all multipliers. And yes, I mentioned this same frequency analysis, but maybe that could be just material for another talk. I think I will just stop here. I will just go to the last slide. Thank you very much for the attention, and yeah, I'm sorry again for the to be late. Yeah.
Okay, thank you very much, Professor Luz Roncal, for your very inspiring talk. For the attendees. So now we are open for questions. So does anyone has a question for Professor Luz Roncal? Remember, you can raise your hand. Using the reaction tool of Zoom, right? Okay. People is happy with your talk, I think. I myself have a question, right? But I should wait maybe. I have many questions, but I should wait. Our attendees. Okay, maybe then I can start maybe asking my questions. Of course, maybe you have considered, right? You have considered the boundedness properties in the case of these maximal functions for your family of multipliers, right? My question is, let's say what happened if one goes a little bit beyond. You put, let's say, pseudo differential operators. Okay, you move to Fourier integral operators, and you consider the problem, right? The boundedness problem for this operator, you know?
Yeah. Well, even in 2 dimensions, I don't know if there is something known, right? Well, I mean, yeah, no, it's a natural question. Just in 2 dimensions, look at because pseudo differential, then you will have like an AXT, right? And then you want to put the direction in AX V times T. To be honest, I don't know if this has been done at all. Maybe, I mean, one should look at, because it's a natural question, of course. No, what is next? And but don't go to the higher dimension. Just start with 2 dimensions, like the pseudo differential analog of the directional Hilbert transform. I don't know. It's a question that one can ask and see what's happening. No, my concern is that I don't know if, for instance, these modern techniques or approaches of time frequency analysis, how could they be adapted? With but yes, it's a good question. It's a good question. Yes, yeah. Yes.
And okay, maybe another curiosity. Okay.
There is one.
I can postpone now. So, Blanca,
Oscar.
I think Oscar. There are several. Sorry. Okay, there are several questions in the chat. Sorry. So I will start with the question of Lamin Barki, who says, in the part single annulus Sigmund Steining codimension 1, which is the importance of Lockhold. Okay, I think it's difficult to maybe can you read the question? Sorry.
Yes,
Lamin.
in the part single annulus Sigmund Steining codimension 1, which is the importance of Lockholder and what happened with this condition. Yeah. Well, I will start here. This is like, I'm going to cheat a bit, okay? I'm going to cheat a bit. In some sense, this is like when you look at Calderon-Simon operators, you need some smoothness. You need some regularity to get some cancellation, right? In some sense, this is happening a bit the same. No, at some point of the discretization in the model operator, you have pieces, you have to look at them, you have to study them, and there is some decomposition, and at some point at certain point you need some cancellation. And this cancellation is essentially saying that you have some smoothness condition or regularity condition or Hölder condition. Okay, so you can think of this is like the analogous to the smoothness condition, cancellation condition in Calderon-Simon theory. Okay, this is natural. And which is important to use Grassmannian here to the multiplier results and maximal operator in your work. Well, Grassmannian is essentially a way to understand a direction in this codimension 1. I mean, could be codimension, any codimension, but actually codimension 1 that is the easiest and still is something. These are the directions. So you look at the direction in this setting, the higher than, or this is the setting we understood to define directional singular integrals, in higher dimension with this Grassmannian giving, each Grassmannian has a vector, right? So this is the way to understand the directions in this setting. This is the importance. Can we extend it to quantum calculus? Well, I don't know what is quantum calculus. Sorry about that. And okay, send you the okay. Yeah, great.
Okay. And then Blanca has a question. Blanca says, thank you for your presentation. Okay, this is a question, very interesting. In the Sigmund-Stein conjecture, what is the issue to get a strong type 2 bounded?
What is the issue? Well, actually, this is given by this Kakeya counterexamples. If you test it in L2, this breaks down. So, yeah, this is essentially. This is essentially the point that the orthogonality of L2 is allowing to get this game, and it breaks down in the sense that in the end you have your operator known bounded by something that blows up. Okay, so
That's the point. Maybe I will unmute to Blanca. If Blanca wants to say something more about. If you want, Blanca, you can unmute yourself. Okay.
No, I was just curious, like what this. There you go. What is the problem? I mean, I haven't checked the conjecture, so this is why I was just curious, because it is always like when it is with type boundedness, there is always an issue with like in a particular counterexample of the particular point. But thank you so much.
Yeah. Thank you for the question. Actually, just one, maybe even one can. Maybe even in the classical work of Pfefferman on the multiplier of the ball, you can see this game because he uses the failure of the directional Hilbert transform to prove that the multiplier in the ball is not bounded beyond. But I think that I mean I should remember. Maybe it's not the best example, but yeah. But the point is that it breaks. It breaks. Yeah, by looking at this orthogonality. Yeah.
So good to see that young mathematicians are very interested in your work. Of course, so maybe I had a question before that was okay. You discussed the L2 weak L2 estimate, right? And later you showed at some point the LP boundedness. Maybe you mentioned, but maybe I forgot. What happened about LP boundedness or weak LP boundedness before the regime P equal 2, let's say, for P less than 2?
Yeah. It's a good question. Actually, for instance, let's pick to the case dimension 2. Okay, remember this lazy Lie for directional Hilbert transform in dimension 2. I said that okay, you have a P boundedness for P greater than 2 on weak type in 2. Good. And then they were restricting to band limited or functions who were supported in a single annulus. Well, actually, I probably was very quick, but I said there has been further contributions, and I mentioned very briefly. For instance, it's not easy to lower the level. And just an example. So for instance, after lazily, like 6-7 years after that, there was a contribution by Bateman in which when looking at vectors, which depending only in one variable, like Vx1, x2 or equal Vx1, still restricting to single annulus, he was able to prove the boundedness all the way to 1. So for P greater than 1, it's okay. Then the next contribution was like, okay, again, restricting vector fields depending only on one variable. Let's try to remove this single annulus restriction. And then there is a contribution by Bateman and Thiele say that, okay, they are able to prove boundedness, but then P is not reaching 1, but P is reaching 3/2. So it's P greater than 3/2. Is this sharp? It's not known. So it's not easy also to say, and the reason is this and that. It's actually a bit mysterious why this 3/2, for instance, is now the threshold in this case, and how to remove. It's not really clear. Yeah. So. So yeah, it is not known if you start putting some restriction, don't put it others, then you can remove, go down. Yeah, because, yeah, this is the point. Of course, if you don't put any restriction, you don't have anything from 2, below 2.
Thank you very much. Thank you very much. Okay. So it seems we don't have more questions, right? So Professor Luz Roncal, thank you very much for accepting the invitation of Karina and Andrea. And
Andrea, thank you very much, Andrea.
Thank you very much, Professor. Nice to meet you.
Yeah, me too.
Right. You were suggested, your name was suggested by Professor Tangabelu, who we meet in Armenia some months ago with Karina. In a nice
very good. Very good. Yeah.
Indian dinner. So okay, so let's move on. Maybe after this very nice talk, I am happy then to pass the chairing duties to Andrea Hurtado and Karina Navarro, who will chair the poster session. So thank you very much.
Thank you very much, everyone. So now we are going to start with our second session of posters to finish the day. After this, we will have our closing ceremony. Now I can see Blanca is already here. she will share with us her poster. Can we just try to share the screen, and after that I can introduce you, Blanca? Can you unmute?
Oh, okay.
Yeah, okay.
Let me see. I don't know. Oh, here it is. There you go. Sure. I think everyone can see it now.
Yes. Can you maybe full screen maybe? Fit to quit. Yeah. Yes. Thank you very much. So now the first poster of the day is a probabilistic construction of Kakeya type sets by Blanca Radillo Murgia. She is a graduate student from Baylor University in United States. She's a fifth year PhD student. So please, Blanca, go ahead. You can start.
Well, thank you for accepting my poster. And well, first I want to thank you, all the organizers, for making this space possible for Latina and non-Latina women in math, like for showing our contribution to this beautiful science. And I'm really happy of that I follow the wonderful presentation by Luz Roncal, because, well, she now introduced us like what is the motivation of learning those Kakeya type sets. And what I'm gonna do in these 10 minutes is basically just, well, trying to make the construction of those Kakeya sets, right? This is a joint work. It's for my PhD, but it's joint work with my PhD advisor, Paul Hagenstein in Baylor University as well, and Alexander Stokolos in Georgia Southern University in Georgia, US. So, well, the motivation, let me just try to make bigger. Just start with the motivation here. The motivation is trying to understand the boundedness of those directional maximal operators, as we were introduced in the previous talk before. So now here, instead of capital B, I'm just gonna call it omega, but that's my set of directions. And just for simplicity, I'm calling this set of directions between 0 and 1, and it's gonna be the slopes. So I'm gonna call the directional maximal operator the supremum of the average of a function, a measure of function f, when R, or the supremum, is taking over rectangles in the plane. I'm just talking about the plane, such that the longest side creates a slope in this direction omega, right, in a point on omega. So the main question is, well, if we can find values of P for which the directional maximal operator associated to this set of directions omega, it's bounded from LP to LP. Right? And as we were introduced in the previous talk, well, unfortunately, depends on the point of view of who, right? Depends who we're talking, because for me, it's really fortunate because we have more questions still to work with, but we don't have a positive answer about this question, right? And of course, I'm not putting any assumption on their omega, so that will be basically the game. Like for which geometry over omega, over the set of directions, my directional maximal operator will be bounded from LP to LP. So, so what I'm gonna do is trying to present a condition in omega such that the directional maximal operator is not bounded, so it's unbounded for any LP, for a P finite, right? So that will be what I'm gonna talk about today. And this construction, or this proof, is based on the construction of Kakeya. I'm gonna call it Kakeya type sets because it's more combinatory probabilistic construction, as the title says. But at the end of the day, it has the same nature as we saw in the previous talk. Like Kakeya said, it will be those rectangles such that the overlap in an area it's extremely small, but outside it's, well, in the previous talk we call it 1, but I'm gonna make some adjustment on some concept, but that's what is the idea. So we are gonna construct those rectangles such that we have an overlap whose area is extremely small, as small as possible, and the spread area, or the area outside, like where they don't have a crazy intersection, is going to be controlled enough. Okay? So let me start with the terminology that I'm going to use, which is basically I'm going to relate the numbers, because my set of directions are numbers between 0 and 1. So I can relate those numbers 0 and 1 with its binary decomposition, and also the binary decomposition as a string, but also as part of the binary tree. Right? So I'm gonna play now binary numbers in terms of strings, as I put it here, or in terms of a subtree, the binary tree. Now here in this binary tree, depends of the branch is the number that represents. So for instance, here can be 0, this can be 1/2 because it's in the first level. In the second level will be, well, the powers, the multiples of 1/4. So this is 0, 1/4, 1/2, 3/4, and so on, right? And also the same, I can translate or reading this binary tree in terms of 0s and 1 because it's binary decomposition. So it's 0, 1, 0, 1, and so on. And as well, I'm gonna try to read and doing taking advantage of this notation. I'm gonna just also include subintervals. So for instance, this branch with a 0 can be also mean the interval from 0 to 1/2, and this another branch or leaf can be the interval 1/2, 1, right? And the same. So I'm gonna cut it. I'm gonna make this translation between intervals, point, and all based on the adic decomposition. And of course, because we can do this translation, I can create a subtree of the binary tree in terms of my set of directions omega. So I'm gonna call it T omega. So it's gonna be the sub-binary tree, which correspond to the association of those directions. And the point is, well, as we saw in the previous talk, if we have a finite Lachinary order set of directions or maximal operator, it's nice. And now we have boundedness for any LP. So the idea is, well, what happens if we have infinity order of infinity order of my Lachinary set. So what is Lachinary in terms of the binary tree? It will be depends of the leaf. In terms of numbers, it's, for instance, order 1 if we are seen as numbers or the sequence of power 1/2. And order 2 if we saw the numbers as the sum of 2 powers of 1/2. And order 3 as the sum of 3 powers of 1/2. In this kind of way, we can see the Lachinary order in terms of numbers, but also we can see in terms of the binary tree as how many splits we have, because at the end, what we are doing with the race and the binary tree is adding the numbers. For instance, this is 0, this is plus 1/4, this is plus 1/8, this is plus 0, plus 1 over 30, what it is, 1632, and so on, right? So basically is when we have the splitting vertices. This is the way that we can read Lachinary. So in the last minute, well, what is the main condition that I'm gonna put to my set of directions that I can guarantee the existence of Kakeya sets is something that we call eta separated condition, which is if I have in my subtree 2 vertices, U and W, right, who comes from a vertex W, right? So the distance, the Euclidean distance between these 2 subintervals, U and W, it's greater than or equal eta times the father, right? The length of the interval of W. The classical example here could be Cantor set. Cantor set, when you are splitting, you are cutting the middle third interval. So the distance the Cantor set, it will be 1/3 separated, because actually the Euclidean distance between the two subintervals we are choosing for the Cantor construction is going to be 1/3. So that's more or less the idea. Now, this is a little bit more general than just these self-affine or self-similar subsets. Is a little bit more general because we don't care about how thin can be U with respect to V. We don't care if one is smaller and one is bigger, but at the end of the day, they must be separated. And if our set of directions satisfy that condition, we know that the maximal operator will be unbounded for any LP. So this depends on the Kakeya set, and as we saw before, is depending on the construction. And then the construction is just basically by sticky maps. And the sticky maps is going to be a map mapping a binary tree to another binary tree, such that the image respect the height of the points, the higher of the vertices, right? And also if U is an ancestor of V, well, the image of U is going to be also an ancestor of V, of the image of V. So at the end, it's basically just following the path, right? That's what is the stickiness here. And we can prove, so we are going to call, or we are going to construct the sticky maps from the binary tree to the subtree represented by the set of directions, omega. Right? So we are choosing the weight of directions that I want to go. And what I'm gonna do for constructing finally the rectangles that represent this Kakeya set will be those rectangles constructed by sigma, by these sticky maps that I'm choosing, but I'm gonna cut, because they are infinite rectangles, so I can cut just from 0 and 1 to have like a small rectangle here. And what will be like the dual in this case will depends of eta, so it's going to be cutting those rectangles in the string 1/eta and 1/eta plus 1. So I have the picture more, you can see more like the picture what I'm doing. For instance, the Cantor set, those are K1 and those are K2, K sigma to, in this case, 1/3. But we can have another kind of example. So where I'm choosing K1 as the area of the rectangles in the string 0, 1, and K2 as between 1/eta and eta and 1/eta plus 1. And well, we can prove, and in the last minute that I have, we can prove the following two theorems, which is basically proving that this construction gives us a Kakeya set. So the area where they overlap, so between 0 and 1, is going to be really big, which in the previous talk we consider a constant 1, but doesn't matter. The point is that we have bigger area, so this will be greater than logarithm log of n over n. And when it's a spread, it's extremely small. So that's the eta, that's the epsilon that we see in the previous talk. Here I'm going to call it 1/n. And because we want to run n to infinity, we will guarantee the maximal operator. And the way that we are going to guarantee that, it's because we can show that the maximal operator acting on the characteristic function of K sigma to eta is greater than a fixed constant for any point in K sigma 1. So if I want to take the LP norm of the maximal operator, well, it's just basically the LP norm of this set K sigma 1 divided by the LP, well, because the LP norm is just the supremum over any function, right? So the particular function that I'm choosing are those characteristic functions, and it's gonna be basically the ratio between the LP norm of the characteristic function over K sigma 1 divided by the LP norm of the characteristic function of K sigma 2, but we have like basically, it's computing the areas. That was what we did in these two lemmas, right? And we do the quotient of these two ratios. Well, we have that is bigger than log of n, and we run n to infinity. So we have that there is no possible to bound it or to create a bound for our maximal operator. Now that, well, we have a more open questions, like, if it is not ADA separated, it still is an open question, so we don't know how to prove or unprove the boundedness of the maximal operator. So everyone is welcome to work in this area. Thank you.
Thank you very much, Blanca. Sorry. Does anyone has any questions? You can raise your virtual hand or write in the chat. Okay, so thank you very much, Blanca. Which it was really a nice poster, and it was like a bit. We didn't do this on purpose. Like, you continue with this topic after Professor Luz Roncal, so it was really a coincidence. So it was really nice.
Yeah, it saved me a lot of minutes.
Yeah, and I wish you a really good luck and success with your PhD.
Thank you so much.
Thank you. So now the second poster of today is by Tim Prokosh. Are you here, Tim?
Yes, I am, and I hope you can hear me.
Yes, now I can hear you. So can we try to share your screen and then I introduce you after that?
Yes, of course. Should work. So I got the PDF at least opened. But do you have to give me some permission?
Yes, I think we make you co-host already. Sorry. Now you are co-host. Yeah, now you are co-host, and then you're able now to share your screen.
Doesn't show me the button though.
Oh. So maybe can you try again? Because you are now a co-host, and then you should be able to share your screen. If not,
I mean, you have the PDF, so
then we
if you can just
share,
open it.
Yes, then we can share, but then we need 1 minute, please. We were prepared for this.
It's always good to be prepared when using Zoom.
Yes. Now. Sorry, I think we have a technical problem because we have really different connections. So now our Zoom is in Mexico, and then the technical support is in Brazil and in Belgium, and then we are trying to share your screen, but it's weird that we're not able to. So just give me 1 moment. Yes. Thank you.
Okay, great. Now it may be a little bit difficult to navigate, but
Yes.
should be
Yeah.
fine.
Okay, maybe just try me to indicate which part of
Yes,
the poster
I
you
mean,
present.
I mean, the things should be big enough to see. So only on the formulas. If I talk about the formulas, zooming in on them may be helpful. Otherwise, everything should be clear, I guess.
Okay, sure. We will do our best.
So exactly, I try to be as minimalistic as possible.
Okay.
Okay, let's start at the top then.
Thank you, Tim. And now I will formally introduce Tim with his poster. Is Entropic Sparse Learning Utilizing Reconstruction on Affine Subspaces? Tim is a PhD student from RPTU Kaiserslautern in the Financial Mathematics group. So welcome, Tim.
Thank you very much. Okay, so yes, as Andrea already said, I'm a PhD student in financial maths, and I did my master's thesis in mathematics in AI, or AI in mathematics. So we care about how we can develop more robust or more reliable small-scale models, which are really powerful and so many different classification, but also regression tasks in a more robust way that is currently possible with, for example, random forests or neural networks. So if we go to the top of the poster, we can see that for typical machine learning algorithms, we have the problem that we need huge amounts of data. So, for example, when training the OpenAI models for GPT 1, 2, 3, and now 4, the energy consumption was enormous, taking the same amount of energy as like 3,000 German households just for training the models. And this is just not feasible and not scalable because energy is a finite resource. So we have to be considerate about this. So if we have, for example, very complex data, for example, huge images or medical data, it is not uncommon that those data sets have very large amounts of features, like in the thousands or thousands. For example, genomics of species like worms, leading to different expressions in each gene and base pair. So you have easily data sets with like only maybe 300, but each set like 25,000 features, each expressing the occurrence of a specific base pair in the genome. And having these many features causes a huge problem because not all of those features are usually important for the task you're going to solve. So for example, if you want to find out some specific phenotype correlated to only a few of the genes, there may be only 2 or 3 genes that cause this expression, but the other 20,000 are irrelevant. So what you want to usually do is also to extract some subset of features which is expressive in this task you're trying to solve. Now, the problem is if we have this huge amount of data, dimensions and features, but only a very limited amount of samples available because medical testing is quite expensive. So it prohibits us to maybe conduct extensive studies, or if it's a rare disease, you may not have just the patients available to generate the data. So the problem is that these huge dimensionality tasks and reducing them is a very hard task in common machine learning, which would require us to have a lot of data available, which we, in this case, just don't have. So the goal we in my previous department and I were trying to solve was designing lightweight models which still are able to produce accurate predictions, with the added feature selection capabilities, so that the model can also tell us, okay, we only need a few features out of the maybe 10,000 that we provide to it. What would also be nice would be to have a model which is also explainable and robust, so that we can actually not have like this black box approach like with neural networks, but actually see, okay, this gene is this much or has this much of an importance to our task, or this parameter in our model tells us that, okay, this and that happens, so that we can really introspect what happens in the data, unlike with neural networks or other black box models. Well, I mean, blowing up the model size would probably solve this problem, but this would impact the training process time. So we would also like to have a model which is fast in training, so that we can try out different architectures or hyperparameters for tuning to find a model that best. Finding a model which is also data efficient, fast in training, explainable, can select features, classify, and be accurate is quite a difficult task, because some of these problems just contradict each other. Like being good at classification, but also a very small model is usually, a contradiction, for example. So in my master thesis, I was building upon a model called ESPA+, which was developed by my supervisor, Ilya Horenko. And this model basically combines the concepts of entropy as a measure of information, the Bayesian theorem of conditional probability for classification, and convex coding, or in the simplified settings, k-means, to create a spatial clustering. So the green term you see is corresponding to the k-means or convex coding. So our S is the matrix of prototypes, which we specify as a number of k. So we have, for example, 3, 5, 4 or so prototypes that we want to learn. Gamma is the assignment to the prototypes. So it tells us, okay, this data point is this much of that prototype, that much of that prototype, and so on. So this is the convex coding term. And this partitions our space or encodes our data in a lower dimensional setting. The red term is used for weighting. So here, and I see the F in the green term, it should actually be a W, because we are not considering the Frobenius norm, but the weighted Frobenius norm. Because what we do for feature selection is, for each feature, we look, okay, how much importance does it carry to the overall classification task or data encoding task? And by using entropy as a concept of information content, we can compute in an analytical way. So without using any numerical solvers, we can compute the optimal weight distribution across the feature space to select the optimal number of features, or at least, if we don't threshold, the optimal weights. So it can tell us this feature has this much information content relative to all other features. And then in a post-processing, for example, we could extract the features which are assigned the highest information content. And the light blue term, well, this is just using conditional probability to solve the classification task. So it takes all points that are assigned to one prototype and averages the assigned labels, which are contained in the matrix pi. And this produces an inference matrix lambda, which then can be used in a further step to classify new points, which we don't know. So for example, if you have a trained model, we have the matrices S for the prototype positions, gamma for the assignments, W for the feature weights, and lambda for the label inference. And if we have now a new data point x tilde, we can first compute to which prototypes it belongs. So we would compute a new matrix gamma using a nearest neighbor assignment, for example, or a convex coding approach, depending on the admissible space that we choose for gamma. And then using this gamma, by computing the product lambda gamma, we get the inferred labels pi tilde for our new sample x tilde. So this label can also be used for classification in this way. Now, one issue of this model is, albeit being very efficient, very fast, and quite accurate, the feature selection has some issues if the data is not nicely aligned. So if we zoom in onto those 3 plus in the middle down there, we can see that the red points are just generated by using a noisy identity. So for example, if we have a 50-dimensional data space and we use just identity function to generate our data and just add some noise, obviously this will lead to a point cloud, which is intrinsically more or less one-dimensional. But because all axes or all features somewhat contribute the same amount to this data set, the ESPA plus model is not able to really extract this one-dimensional structure because it can't see that it's residence. So when training this model, what we observe is that it considers all dimensions to be roughly of equal importance. What I did then in my thesis is, okay, instead of looking at the original data space, what about looking at a transformation of our data space? And this is what the green axis in the red on the left indicates. So if we just use a transform of coordinates, we can generate a new coordinate system, x1 tilde, x2 tilde, and so on. Here, obviously, I only show the first 2 dimensions because it's the poster. But just imagine there's just d minus 2 further dimensions that all look the same because it's the identity. We can see that the largest amount of variance is attained along the axis describing x1 tilde, and all other dimensions have rather small variance. And if we now run the model on this transformed data set with the new data, with the new coordinate system, we would obtain an image like the one on the far right with the green stem plot. And in this case, the model is actually able to determine that only one feature really is necessary for the encoding part. So in this example, I left out classification because the issue occurs no matter if we want to classify or not classify. So even in the simpler setting of a unsupervised learning algorithm, we face this problem. So obviously in a supervised setting, we would also run into this issue. But if we apply this transform of coordinates, we can see that indeed the model is able to single out the first feature as the only one that contributes to the spatial structure of the dataset. And this transform of coordinates is exactly what is computed by PCA, basically. Because PCA gives us a new coordinate system, which we can specify the number of feature of by using or by specifying the number of principal components that maximizes the variance captured by the first K or first D tilde dimensions that we want to have. So the idea of this model extension is to just replace the green clustering term in the loss function of ESPA plus by the modified term used in principal component analysis. So if we take a closer look at this ESPA using reconstructive subspaces, that's why the poster got its name, because PCA not only is maximizing, but there is an equivalent formulation which works based on minimizing the reconstruction error caused by projecting onto the span subspaces. And hence this formulation using projections fits better into our framework of linear algebra, which we're using for model derivation. I chose the name of reconstructive subsurfaces and not maximizing variance. So the first term that we added or modified was the green term. So the first term, the weighted reconstruction, basically just takes a projection matrix P, which consists out of the identity subtracted from Q times Q transposed, where Q is just the columns describing the principal components. So the matrix P is a direct product or result from applying the PCA algorithm to our data set. Now with the matrix W, we just apply them for every prototype. So we just localize our feature selection to get a more fine-grained feature selection process. So the first term basically just applies PCA, including the entropy optimal weighting and k-means. And since we can do this in one optimization step, we do this iteratively, like in a splitting approach. We first optimize Q, then W, then gamma, then mu, and repeat. Q, so we just swap and cycle through our parameters and always compute the optimal solution with respect of to one of them while fixing the others. And because we can compute these solutions for the most part in a closed form way, so we have an actual expression which we can efficiently compute, we are guaranteed to a sequence of loss values. And because our loss function is also bounded from below by some value, we are actually guaranteed to have monotone convergence. So the model is guaranteed to converge, and we can also bound and estimate this minimal loss, which is in contrast to obviously neural networks which have no monotonic convergence guarantee whatsoever, which makes this quite nice because we can just specify a tolerance and see if our parameters W, gamma, mu, and S, not S, lambda, which is hidden in the ... because it's the same as in the old model. If they just barely change, we are guaranteed that the model will not improve any further. The second term I added is the distance penalty, and we will see soon why this is important. Because our subspaces, they are unbounded, and by adding a distance penalty, we can shrink them down. And this epsilon b is just a regularization parameter which tunes the amount of shrinkage that we want to apply. Obviously, if we set it to 0, no shrinkage is applied, and the subspaces span infinitely far away, which is usually bad. In contrast, if we choose it like very big, close to infinite, the only thing that we are consider is basically, again, nearest neighbor assignment, which is bad for the reasons we had earlier. So the sweet spot for this tuning parameter is somewhere in the middle and could be figured out using, for example, Bayesian optimization, grid search, or some other hyperparameter tuning algorithms. If we now take a look at the graphic on the right with the spirals, the top of the 3 ones, I tried to simulate this shrinking effect. So the plot on the left shows what happens if we don't use epsilon b at all. So the lines, the black lines, the subspaces which are spanned by the model, and they crisscross all over the space. And with the accuracy of 78% on this data set, which is quite bad. By increasing this shrinkage parameter to 1, we can see that the black lines get closer and closer to the center of them, basically shrinking the extent of the subspace. And we can see by increasing it to 1, we managed to get an accuracy of 98.2%. So getting much better than before. On the other hand, by shrinking them too much, we can see that the extent of the subspaces is too small to capture all the detail of our data set. However, if we choose it a little bit smaller with a tuning parameter of 0.2, the subspaces are just big enough to capture all fine detail, yet small enough to not interfere with each other. And this actually gives us an accuracy in prediction of 99%. So even better than choosing the parameter larger, thus reducing to a more nearest neighbor-y assignment procedure. In the plot below, I investigated, okay, how does this parameter affect how many prototypes I need the model to be able to place in our feature space to reach some given accuracy threshold. And especially the green line is of interest here. This specifies a accuracy threshold of 99%. And what I tested in this case is how many prototypes do I need to give the model to be able to reach this threshold of accuracy? So how many centroids or prototypes does it need to place to be able to reach an accuracy of 99%? Independence of this fine-tuning parameter, increasing or decreasing the shrinkage of the subspaces. And we can really see that there is an optimal point in between around 0.1, where the subspaces are shrunk just enough to be able to capture the detail, yet are not big and too big to interfere with the other subspaces. If we decrease the parameter, we need a lot more prototypes because the interference impacts our classification capabilities too much. If we increase it, then the subspaces are shrank too much. So we need to place more prototypes again to tile the space appropriately. Now, this is all nice if we apply it to synthetic data, which is two-dimensional and so on. So to test how this model on a complex data set, I generated using the Lorentz model, which is basically some toy model modeling some atmospheric dynamics. I generated a trajectory of pressure, air pressure. Yes.
Sorry, Tim.
Yes.
1 minute, just to
Perfect.
remember. Okay, thanks.
That's perfect. So what I did is I generated a trajectory, which is chaotic, as you can see. It's not periodic, it changes behavior slightly. And using some data generating process, which takes into account the past data and some other quantities which you can extract from this trajectory, I trained this model to predict 20 days ahead, which is the red line. And I colored the plot according to how big is this deviation from the true value. Obviously, because it's a classification model, I have to discretize. You can theoretically also do this with a regression model, but I didn't have time for this in my thesis. So I went with the discretization approach and implemented it as a classification problem. And as you can see, the model performs decently well. The most of the part, it follows the trajectory quite well. Only in some parts, okay, predictions are not too good, which is to be expected from a chaotic system. In my thesis, I showed also a comparison to SVMs, neural networks, and random forests as an ensemble method. And it could be shown that, in fact, this entropic PCA model was beating all of them with flying colors in this problem setting, just because it was able to extract the relevant quantities for prediction much better than the state-of-the-art models which are used in everyday life nowadays. Thank you very much.
Thank you very much, Tim, for your nice presentation, for your time, and yes, for being here. It's really already late in Germany. So for the moment, we are really tight with the time, so we will not have time for questions right now. But if anyone has any questions or is interested in Teams or the following poster sessions, then you can just write an email. Their emails are in the book of abstracts, and I know they are really open to have this discussion, so it will be really nice. So thank you very much, Tim, again for your nice poster. It was really nice colors, nice presentation. And now we can continue with our next poster. It's by Ayla Nurkanovic. It's Optimal Investment and Sustainable Taxation. Ayla is a PhD student from RPTU Kaiserslautern in the Financial Mathematics group also. Welcome, Ayla. Can you hear us?
Yes, I can hear you. Can you see my poster?
Yes, I can see it. Thank you.
Okay, perfect. Thank you for the introduction. So yeah, I'm from the same university as Tim and actually in the same working group, so financial mathematics. And I'm doing my PhD on the topic of sustainable portfolio optimization. We will see in a moment what that is. And today I will present to you that topic, so sustainable portfolio optimization, and one other topic that came from that one that we called sustainable taxation. Here I have some main take-home message, but I will get to that at the end. I will not go into much mathematics because I realize that we come from various different fields. So I would rather that you understand the problem that I'm dealing with and why am I dealing with it. And then hopefully, then if you're interested about more mathematics behind that, as Andrea said, you can always contact me, or if there is time for questions, let's see. So first of all, I'll start with the motivation. This all started with a law that was introduced in Germany in August 2022 when it comes to pension products. Namely, now customers that want a pension product, they have to be asked by a provider about their willingness to invest their money in sustainable assets. And now that proposes new challenges for the life insurer. For example, the main one is how to optimize returns while keeping this desired sustainability. Now, as I said, I'm aware that we come from different fields, so maybe some of you don't even know what portfolio would here be or how a pension product works. So I'll just like to explain that briefly. So a pension product works in that sense that, so you basically want to have an extra pension later in your life. So first of all, a customer is paying to the insurer for one amount of time, some amount of money. And the insurer, before they actually pay out that money later as a pension, they invest that money so that they make more money out of it because they want to, for example, give an attractive pension later. If you imagine, those are years in between, so there's also inflation, so that's why it's important to make more money out of that money, and also there are other costs they have to cover. So that is the portfolio that we're talking about. That money from the customer that the life insurance is then investing. It's investing, for example, in 3, 4, I don't know how many different stocks, and it's something that is called a life insurance fund. That is something that is riskless. So that in what he is investing and how much, that is basically the portfolio. So here I'm going to show you now the basic portfolio setting, which is basic for any portfolio optimization. And then I will get here to the modeling of sustainability, which is something that is new what we did. So first of all, as mentioned, here we have what life insurer is investing in. So there is life insurance fund. So that's a riskless investment. It's like a bank account. Let's say B0 is the amount invested into that at the beginning. And then if we know that R is an interest rate at time T, we know that we have this much money in there. With stocks, let's say stock SI, it looks like this, how it's modeled. This BI is in red here because it will be important later. At the moment, I just want to say that we know that stocks are stochastic, there is risk in there, so they are modeled here as a geometric Brownian motion. We have a Brownian motion here, which gives us that behavior. Then we have a portfolio vector, pi, which we write as pi1 to pi n if we have n funds that we're investing in. So what is pi1? It tells us how much of the wealth we are investing exactly in the stock or fund number 1. So let's say 1/3 of the wealth we are investing there. So pi1 is 1/3. And I want you to remember that X is the wealth process of the investor. That is what we want to maximize. Okay, so here now we have the sustainability modeling. So as I said, now the customer says how much they want their portfolio to be at least sustainable. So when it comes to that, we have to know that not everything is just completely sustainable or not sustainable at all. It can be, for example, it can have a rating how much a certain company, a certain stock sustainable is. And there exists ratings like that. For example, Bloomberg has an ESG score, which gives a score from 0 to 100, where 100 is the most sustainable something can be. And then we take those ratings, but we scale them from 0 to 1. And RI is, for example, a rating of our fund I that we're investing in. Then we define a portfolio sustainability, which is going to be the sum here. So let's say we have 2 stocks that we're investing in. For example, we say we will invest 1/3 into the first stock and 2/3 in the second stock. Then our portfolio rating is going to be 1/3 times the rating of the stock 1 plus 2/3 times the rating of the stock of number 2. And then we have demand, which is also between 0 and 1, and so is this R pi. And our new sustainability constraint is that we want that the portfolio sustainability is at least as high as the customer's demand for sustainability. Okay, now let's get to the part of the problems. So a classical optimization problem looks like this. We want to maximize final wealth. There is here E, that's expectation, because we have stochastic behavior modeling. And there is this U utility function. I'll not go into detail, just say with that function, we can model how risk-prone our customer is, because not everyone is risk-prone the same. Some like to risk more, some like to risk less. And for example, in this classical optimization problem, the solution, we will name it pi star, and that is well known, that solution. My problem now is sustainable optimization problem, where not only that I want to maximize this, but I also want that my portfolio rating, sustainability rating, is greater or equal than the customer's demand. And what I get then is the solution that I call sustainable optimum, I star S. So of course, adding a new constraint makes this optimum suboptimal to the one from the classical problem. So you could ask, well, isn't that then unattractive to do that? Well, there are various reasons to believe that this is actually still attractive, and it's going to just become more and more attractive in the future. We have demand for higher quality of living, which is growing. We have upcoming taxation of non-sustainable industry. We are slowly running out of non-sustainable industry. And the thing is that the sustainables, after a build-up phase, they promise high future returns. So that is one problem. And then we came up with another problem. So we have this classical optimization problem. And what I want now is I want to see what changes can I do to the vector B? And B is the mean return of the stock, so it's this B here. How can I adjust that B such that when I'm solving this classical optimization problem, so I'm just maximizing this, I get a solution which is actually from this problem. So I get a solution which is already sustainable. I get a sustainable optimum. So basically why we name it sustainable taxation, it's because this could mean that if we are making B smaller, it means like we are taxing the company because it probably isn't sustainable enough. Or we could also, if we are making it higher, that would mean that we are subsidizing the company for being sustainable quite well. So it's a little bit of misuse saying that it's sustainable taxation, but I hope you get my point. So I'm gonna just quickly go a bit through results. What I did then is I solved these problems. I got formula for pi star S and for this adjusted B for two different utility functions. Then I was seeing how B tilde, this adjusted B, behaves under different changes of different parameters. And I saw that that highly is dependent on the ratings, of course. And I did quite some numerical analysis. And what I saw is that already for two stocks, we can see some very complicated behaviors. And that actually just motivates this research further. So I just want to give a bit more of takeaways. So what I presented to you today is something I called sustainable portfolio optimization and also something called sustainable taxation. Sustainable taxation we saw that was just introducing this hidden tax on the portfolio as an aim to induce market behavior that supports sustainability. On the other hand, when it comes to sustainable portfolio optimization, I just want to mention here two more interesting facts before I go into that, is that life insurance assets in Europe in 2017 were 7.5 trillion euros, and that 71% of Germans believe that insurance companies should indeed promote sustainable behavior with their products. So that means that even if this demand is small, and even if not everyone wants to actually demand this demand, it's still a lot of money, and taking a small fraction of that, it's still a lot of money going to sustainable. So here, one more reason why I was talking about life insurers is because actions with sustainable impact often require long-term investments, like for example, solar or wind parks. And that is exactly in line with strategies used in pension funds, at least with respect to their duration. And indeed, life insurers are actually buying solar and wind parks because of that. And insurance companies, because of that, have a potential to offer pension products with significant sustainability component. When it comes to this sustainable portfolio optimization, you can find our paper on that topic here, and the one on sustainable taxation is at the moment under the review. And at the end, I just want to come back to the main message, and that is that one here, that life insurers and pension funds are the perfect partners in the transformation of today's industrial societies towards a more ecologically oriented form. Thank you.
Thank you very much, Ayla, for your nice poster and for your time. Yes, for the moment, we are running out of time because our closing ceremony is at 7:30, and we have some delays in some talks after 5. But it was a really nice poster. It was a really nice presentation, and thank you very much for joining us.
Thank you. Thank you.
Today.
And
if someone is interested in her work, you already say it, you are welcome to contact her. She has this email and her LinkedIn page. Also, her email is in the book of abstracts. So you are welcome to contact her if you are interested. Thank you very much, Ayla.
Thank you.
See you. Ready?
Yes. So, okay, we will continue with the, let me check the time. Okay, two posters left right now, but I think it's better if we continue to after to the closing ceremony. Okay, so we will return in 5 minutes to the closing ceremony, and we will continue with the scientific program in 5 minutes. Okay, so see you soon.
Hello, Astrid. How are you?
¿Puedo iniciar?
Okay, well.
Ok.
Okay. Bueno, ha sucedido que tenemos un pequeño delay, un pequeño retraso que se produjo desde una sesión anterior, ¿cierto? Entonces, ¿me escuchas bien, Astrid?
Sí, te escucho
Ok.
perfecto.
Ok, entonces, ¿qué te parece? Te pedimos disculpas por esto. ¿Qué te parece si nos das tiempo para iniciar con la ceremonia de clausura? Y luego de la ceremonia de clausura, entonces continuamos con la presentación de tu póster y del póster de el otro investigador joven que está también programado. ¿Tienes algún problema o te parece que
No,
estaría bien?
no, está bien.
¿Te
Perfecto.
parece? Vale.
Ok.
Entonces vamos a proceder de esa manera, ¿listo?
Abren la puerta hacia un mundo de... En el corazón de América Latina, nuestros proyectos trascienden fronteras para construir un futuro de descubrimiento, innovación y transformación. Bienvenidos, nosotros somos ICMAM Latin America, donde las matemáticas abren la puerta hacia un mundo de posibilidades.
Okay. Okay, so we are back. As we come to the conclusion of the ISAAC-ICMAM Women in Mathematics 2024 conference, I would like to express my heartfelt gratitude to all of you who have joined us in celebrating the contributions of women in mathematics. It has been an honor to share these 3 days with all of you. So thank you so much. Okay, let me check. The Professor Irene Maria Sabadini is here. I am very happy. Okay. Okay, 1 second. Sorry for the delay, but okay. One second. Okay, so we are going to start with the closing ceremony of the ISAAC-ICMAM Conference of Women in Mathematics 2024. Let me show the plan of the ceremony. Okay, so we are going to have some words by the Professor Dr. Irene Sabadini. The Professor Irene Sabadini is the board member, secretary and treasurer of the International Society for Analysis of Application and Computation, ISAAC. After that, we are going to hear some words by Duvan Cardona, the scientific director at ICMAM Latin America. Okay, so it's my great honor to introduce the Professor Irene Sabadini, whose remarkable work continues to inspire. Professor Sabadini, thank you for being with us. You can start.
Thank you. Can you hear me?
Yes, we can.
Thank you. Good evening or good afternoon, dear colleague, according to your local time. I'm very honored to have been invited to this closing ceremony of the ISAAC-ICMAM Women in Mathematics 2024. And I'm grateful to the organizers for this invitation. And I'm also grateful to them on behalf of the ISAAC Society for all the work they have done to make this event possible. In particular, the list of speakers is truly impressive and shows how many of our women colleagues are active in cutting-edge research in mathematics. I thank all the speakers for participating and for contributing to the success of this conference by presenting their work. And I also thank all the participants, especially the women, to whom this event is dedicated. I have to say that while thinking about what to say during this closing, I realized that in fact it is necessary to speak more to men sometimes than to women. In fact, very often the success of a woman who has a family is linked to how much help she can find at home, and therefore how much time she has left to carry on her work. And moreover, to have time for a woman also implies the support of her institution to have adequate infrastructures available. From this point of view, I believe that every woman must act as an ambassador to help obtaining the needed support and infrastructure. I wish all of you to have enough time for your research and to find adequate support of it. Thank you again for your contribution as a speaker or as a participant, and goodbye. And thank you again to the organizers.
Thank you. Thank you so much.
Professor
Irene. Sorry? Okay. Okay, thank you. Okay, so now continue with the program to this closing ceremony. It's my great pleasure to introduce the Dr. Duan Cardona, our scientific director, ICMAM Latin America. Please go ahead, Duan.
Okay. Thank you very much. First of all, thank you to Professor Irene Sabadini for the very inspiring words. Okay, I will take the time maybe to share some words, right? As a representative of ICMAM Latin America. You know, as we gather here today at the close of this remarkable conference, I ask you to take a moment and reflect not just on the ideas exchanged, but on the power of what has been created here this week. This event has been far more than a collection of talks. It has been a declaration and a statement that mathematics belongs to everyone, that talent knows no borders, and that our field is stronger when it embraces the voices of those who has been too often overlooked. When ICMAM Latin America began in 2020, it was born from a dream, a necessity, and perhaps even a quiet rebellion. A dream of building a community for mathematicians from Latin America, many of whom felt invisible on the world stage. A necessity to create opportunities for those who had none. A rebellion against a history that too often told us that voices from the margins don't matter. And yet, here we are, just 4 years later, this dream has crossed oceans, broken barriers, and rewriting narratives. From Colombia to Europe, from virtual spaces to physical ones, ICMAM Latin America has become a bridge connecting people, ideas, and futures. This week, we did something extraordinary. Women mathematicians from every corner of the world coming together to share their work and their histories. These women, whether emerging scholars or established leaders, are proof that change is possible. Their presence here is a testament to resilience, brilliance, and the power of collaboration. But let us not forget how far we have come. Just few years ago, the idea of Latin American organization receiving support from the International Mathematical Union or the support of ISAAC seemed distant, if not impossible. And yet, here we are organizing conferences, publishing books, and supporting projects that are changing the mathematical landscape in our region. Aim on this project is the book led by ICMAM's Women Mathematicians, a collection of works that represent not only research but also courage, a refusal to be invisible. And this courage was present in every discussion, every lecture, and every question asked this week. Let us leave this conference with a sense of responsibility. The work we do here is not just about mathematics. It's about changing lives. It's about opening doors for the next generation of mathematicians, especially for the young women who may one day stand where we stand now. To those who organized this conference, Andrea Hurtado, Karina Navarro González, Yuriko Pitones, and Milton Aguirre, you have shown that it's possible. You have shown what is possible when passion meets purpose. You have not just planned an event. You have made history connecting ISAAC and ICMAM Latin America by the first time in a joint conference. And to everyone here, remember this. The equation we solve may one day change the world, but it is the connections that we build, the opportunities that we create, and the courage that we inspire that will truly stand the test of time. This is not just the end of a conference. Our organization, ICMAM Latin America, continues working hard, and it is the continuation of a movement for inclusion, for representation, and for excellence. Let us carry this spirit forward into our work, our classrooms, and our lives. So thank you very much, and thank you to all our speakers that we had in this conference. Thank you to the scientific committee, to Professor Ewe Kaller, the president of ISAAC, to Professor Sundarantanga Velu from the Indian Institute of Science, and the other members of the scientific committee. And especially thank you very much to our organizers. So now I will pass the word to Karina Navarro.
Thank you so much, Duvan. Thank you so much. Okay, so now to finish this closing ceremony, we are thrilled to announce that the ISAAC-ICMAM Conference of Women in Mathematics will return the next year, 2025. So we are excited to share that once again. The conference will be held virtually, allowing us to connect with a global community of talented women in mathematicians. Sorry. We look forward to welcoming you all back to another inspiring and informative event. Thank you very much for joining our broadcast during these 3 days. We have, on behalf of the ISAAC-ICMAM Conference of Women in Mathematics 2024, that you have enjoyed this event. To close the event, this conference, we have still 2 amazing posters, right? So, the first poster for this final part is the dual projective line by Astrid Contreras Mendoza. So, yes. So you can start, Astrid, and thank you for wait. Thank you. You can start.
Buenas tardes, mucho gusto. Mi nombre es Astrid Contreras. Bueno, en esta oportunidad los saludo desde la ciudad bonita de Colombia, Bucaramanga, y quiero hablarles sobre la recta proyectiva dual y compartirles algo acerca de lo que estudié en mi tesis de maestría, que fue dirigida por la profesora Claudia Granados en la Universidad Industrial de Santander. Antes de iniciar, pues me gustaría agradecer al comité organizador por permitirme el espacio de dirigirme a ustedes y a los asistentes y compartir este resultado sobre mi tesis de maestría, y además por la iniciativa de incluir cada vez más a las mujeres en las matemáticas. Bueno, el objetivo principal básicamente es el siguiente. Los espacios proyectivos usualmente se le asocian a los espacios vectoriales. Entonces, en realidad tomamos esta idea y fue generalizarlo a lo que son los anillos, utilizando la estructura de R-módulos. Le quitamos la estructura de espacio vectorial y lo pasamos a R-módulos. Definiendo la recta proyectiva, nosotros vimos que se puede definir una correspondencia sobre la recta proyectiva dual. Y además, cuando yo defino esa correspondencia por medio de se conoce como una correlación, esa correlación me genera o le puedo asociar lo que se conoce como una forma bilineal que le da una estructura simplética al R-módulo. Entonces voy a iniciar con los preliminares. Acá pues vamos a trabajar con R un anillo y M pues va a denotar lo que es un módulo libre de rango 2. Definimos una base para el módulo y tomamos dos elementos y definimos la siguiente operación que la denominamos producto exterior. Este producto exterior, tal como está definido, es inmediato que se puede probar que es una forma bilineal y antisimétrica. Además, con ese producto exterior, yo voy a definir lo que son los elementos que yo digo, los que defino o definimos complementables, que van a ser aquellos elementos a los cuales puedo encontrar otro elemento en el módulo que me completen una base para el módulo. Un ejemplo muy rápido es el par 3,5 en el Z-módulo Z2. Son primos relativos y por un resultado de teoría de números sabemos que podemos hacer una combinación lineal del 1 y eso me va a generar todo el módulo. Bueno, entonces, retomando la idea del espacio vectorial, cuando yo defino la recta proyectiva, nosotros tomamos el espacio vectorial y le quitamos un punto que es el 0, 0. Acá vamos a quitar los elementos no complementables. Entonces, esto lo vamos a anotar como los elementos no complementables. Tomamos el R módulo y le quitamos ese conjunto y lo vamos a partir de esta relación de equivalencia. Cuando yo hago ese cociente, yo voy a detener lo que voy a denominar la recta proyectiva asociada al anillo R. De forma análoga, yo puedo hacer lo mismo para definir la recta proyectiva dual. Acá, pues, el dual, pues, van a ser aplicaciones con esta característica. El kernel va a ser unidimensional, es decir, va a estar generado por un solo elemento y además ese elemento tiene que ser complementable. La relación de equivalencia varía un poquito. Acá vamos a decir que dos aplicaciones van a estar relacionadas si el kernel coincide. Cuando yo tomo el conjunto de las aplicaciones y lo parto esta relación de equivalencia, voy a denominar lo que es la recta proyectiva dual. ¿Listo? Entonces, ¿cuál fue como el resultado? Entonces, nosotros definimos este conjunto que lo denotamos como X y este conjunto es el conjunto de los submódulos que van a ser unidimensionales y complementables y definimos estas dos funciones. Estas dos funciones resultan ser unas biyecciones en los espacios respectivamente, el proyectivo y el proyectivo dual sobre el anillo. Y a partir de definir esas dos funciones, nosotros podemos hacer que este diagrama conmute. Cuando este diagrama conmute, esta función gamma la vamos a llamar una polaridad nula y resulta ser una correspondencia propia, también se le conoce como una proyectividad de Stout, y es muy importante porque es una aplicación que me permite mantener elementos invariantes en los espacios proyectivos. Al definir esa función y al ser propia, yo puedo afirmar lo siguiente. Va a existir esta phi que va a ser un isomorfismo tau semilineal, donde tau va a ser un automorfismo y va a estar definido de la siguiente manera. Entonces, de R2 al dual, y a esta phi es a la que le puedo asociar la forma bilineal antisimétrica que nosotros vamos a llamar H. Tal como está definida H, que está en términos del producto exterior, se afirma de una vez que es bilineal y antisimétrica. Ahora, para ver la parte de la estructura simplética, entonces yo debo comprobar que la H que mencioné o definí hace un momento debe ser no degenerada. Para eso se utiliza la proposición número 8 que me dice lo siguiente, que si yo encuentro una aplicación, ¿sí?, entre el espacio proyectivo dual y el espacio proyectivo, si eso es un isomorfismo, entonces la forma bilineal asociada a esa gama, pues resulta ser no degenerada. Y pues eso era lo que decía el teorema número 4, entonces tenemos que H cumple con las características de ser bilineal, antisimétrica y no degenerada. Y ya pues con eso se concluye que esta expresión que es una estructura simplética. Y bueno, básicamente eso era lo que quería compartirles en este póster. Algunas de las referencias, los detalles y la demostración pues de todo lo que acabo de mencionar, incluyendo más ejemplos y con un poco más de detalle lo que acabo de comentar, está en mi tesis de maestría. Y este resultado específicamente lo escribimos de tal manera que pues estamos intentando hacer una publicación en la revista de Sao Paulo. Entonces el artículo ya fue sometido, está en revisión y esperamos pues que pronto nos respondan que es aceptado. Nuevamente muchas gracias a todos por la atención, por la espera y hasta pronto.
Muchísimas gracias por tu increíble póster, Astrid. Te pido nuevamente disculpas por haberte hecho esperar, pero bueno, son cosas que pasan en vivo y es eso. Muchas
No,
gracias. Tú eres de la Universidad Industrial de Santander,
sí,
¿verdad?
señora. Sí, yo soy
Increíble.
egresada de la
Ujú.
Universidad de
De
Santander.
la UIS, de la
Sí, señora.
famosísima UIS. Ujú.
Sí, señora.
Excelente. Bueno, pasamos a las preguntas. ¿Alguien tiene preguntas? Puede levantar su mano virtual o escribir en el chat. Does anyone have any question or comment? Or you can write on the chat also. Okay. If not, thank you very much, Astrid.
Quizá tengo
The one.
una pregunta.
Okay.
Una pregunta. Quizá, okay, I will make the following question in Spanish. Okay, by following the same spirit of the questions we did yesterday to our female participants. Astrid, entonces una pregunta digamos en el campo de investigación que nos presentaste hoy, seguramente hay problemas abiertos que te interesan, ¿verdad? Entonces, mi pregunta es, ¿cuál de esos problemas abiertos te gustaría resolver pronto?
Bueno, sí, hay muchas preguntas porque, digamos, la idea es quitarle más estructura al anillo, ¿sí? Entonces, hasta el momento, pues hemos podido definir la recta proyectiva y se comporta muy bien, pero cuando el anillo es un anillo total de cocientes, ahí, perdón si lo olvidé mencionar en el póster, pero nos gustaría definirlo sobre otro tipo de anillos, entonces hay que definir los elementos. Los anillos totales de cocientes se pueden trabajar muy bien porque o los elementos o son unidades invertibles o son divisores de cero, entonces uno ahí los puede separar muy bien, pero cuando yo tengo otro tipo de estructuras como los polinomios y todo eso, entonces ya es muy difícil, digamos, definir un producto que me permita cómo separarlos para poder hacer esa definición. Entonces, pues el objetivo es intentar quitarle estructura al anillo y hacer la forma pues análoga a la que hicimos con los anillos totales de cocientes. Intentar definir la recta proyectiva y la dual. La dual, nosotros le revisamos eso. La dual estaba como escrita, ¿sí? Solamente como que habían muchas afirmaciones que se podía, pero no se definía completamente, tampoco habían ejemplos y no entendíamos cómo era el comportamiento de la dual. Casi toda la parte de la recta proyectiva dual fue de nosotros, ahí nosotros pudimos definir y buscar el puente, porque es más fácil calcular la recta proyectiva sobre un anillo que calcular la dual, pero si yo conozco esta por la relación, pues voy a conocer muy fácil la otra. Entonces, la idea es quitar la estructura al anillo para poder, digamos, mirar a ver si se siguen cumpliendo o qué cosas pueden cambiar.
Muchísimas gracias.
Ok, gracias por la pregunta.
Okay, thank you so much, Duban. And thank you so much, Astrid, for your very nice exposition, very nice poster. Okay, we will continue if we don't have more questions. We will continue with the last poster presentation. The last poster presentation is about reconstruction of two-dimension simple manifold from a label set using shape gradients by Chafikuden. Okay, so you can start.
Okay, can you hear me, ma'am?
Yes, we can.
Okay, I will share my screen.
Okay, please.
Is it visible?
Yes, we can see.
Okay, thank you. First of all, I would like to thank for giving this wonderful opportunity. My name is Shafiquddin, PhD scholar, SRM University, Andhra Pradesh, India. My topic is diffeomorphic reconstruction of 2D simple manifold from a level set using shape gradient. We know that the reconstruction of 3D image is very important and crucial in both computer graphics as well as medical field. But accurately reconstruction complex surface such as human brain cortex remains a challenging aspect in image processing. That's why we are developed a mathematical model based on the PDE for reconstruction this kind of complex 3D image. We can say simply we can say that is 2D simple manifold. Also, we implemented an algorithm that is utilized the shape gradient to reconstruct this kind of complex structure. That is, our method is shape gradient method. That is, we introduced a energy function, and we will start with a triangulated surface. Then we know that the vertices of each triangle, and using this energy function, we are updating each vertices according to the shape gradient of the corresponding energy function. Before I will give simple example for the shape derivative of the functional. If you are considering j of gamma is a shape functional, then Euler derivative is defined as dj omega according to the velocity vector, that is limit t goes to 0, 1 by t j of gamma t minus j of gamma, that is normal Eulerian derivative. For example, if we consider that j of omega is the shape function, that is the volume of this domain, then corresponding shape derivative is defined by integral over gamma v of 0 dot n cap. That is, n cap is the unit normal vector to the surface. Next, if the function, suppose y is a function from Rn to R, then corresponding, if we are taking the shape functional as a j of omega equal to integral over omega y dx, then corresponding the shape function derivative of this functional, that is integral over gamma y v of 0 into dot product with a, that is normal vector. And here also, here not gamma, sorry, this is mistake, j of gamma equal to integral over gamma. If we can consider the that is surface integral also, that is integral over gamma f into d gamma. If we say any function from Rn to R, then corresponding shape derivative is defined by integral over gamma grade f, that is gradient of this corresponding function dot product with a v of 0. V of 0 is the instantaneous velocity vector, that is plus f into, that is tangential divergence v of 0 dot n cap. This is some basic result in shape derivative. Next, I will introduce our mathematical model. That is, our energy functional or mathematical model is defined by E of gamma equal to, gamma is the any surface. That is, E of gamma equal to integral over gamma phi square gamma alpha plus beta into mod tangential grad phi square d gamma. Here gamma is the any triangulated surface, that is our, we can say that initial, we can take initial sphere, that is triangulated sphere, and phi is the level set function, that is signed distance function with respect to our 3D data or ground data. And alpha beta is the control parameter with respect to these two parameter phi square and this tangential gradient. Then corresponding shape derivative I calculated as dE is the shape gradient, that is equal to h into, h is the mean curvature corresponding each vertex, that is h into phi square alpha plus beta, that is mod tangential grad phi square plus beta divided by 2, that is directional derivative, that is dou phi divided by dou n, n is the normal vector corresponding to surface into n plus gradient of phi square alpha plus beta, that is mod of tangential grad phi square plus beta divided by 2. Next, that is square of the directional derivative with respect to now normal vector into d square phi square. D is the assign operator. This is the mathematical model. For experiment, we started with a initial sphere, that is sphere with the radius. For the experiment, we collected some collection of phantoms, that is for checking the our model is working or not. First, we created a 3D data corresponding to unit sphere. Then we started with a sphere, that is triangulated sphere with a radius 3. And we are just to calculate the energy in each iteration. This first figure is showing, that is 20th iteration. In 20th iteration, we started with a radius 3 circle sphere. But within 20th iteration, it is the radius is reduced to 1.5 centimeter or unit. After that, in about 100 iteration, second figure is showing with 100 iteration. During this iteration, the energy is minimizing. That is, we have to find this or energy functional. We have to find the surface with minimum energy. That is, using this shape gradient, we formulated our algorithm. Next, within 100 iteration, this initial sphere exactly matched with our ground data, because we are already took the unit sphere as our ground data. This initial sphere is convergence within 100 iteration. It is completely convergence to our ground data or ideal sphere. Next, we took the ellipsoid with a specific dimension. Again, we started with the same sphere, that is radius 3 radius sphere. Then within 20th iteration, the energy is 253, and within about 200 iteration, it is exactly matched with our ground data or ideal surface. Similarly, we checked with the depressed sphere. Depressed sphere means a sphere with a small depression. Again, we formulated the same experiment, that is in a 20th iteration, the energy is 42, but during the iteration, the energy is decreasing also. About 194 iteration, it is exactly matched the our ground or ideal surface. Similarly, same procedure we are used for cylinder also. For after that, we took a very complex surface. We know that our brain is very complicated structure. It contains a lot of folds and gears and sulcus. I took a white matter, that is a gray matter, that is a surface of the brain, that is called the cortex. I took this cortex as our 3D data. We are again experimenting with this cortex, that is very complicated structure. Again, we started with a corresponding big surface sphere. After that, that is we can see that first iteration, the energy is big, that is very large number. After 100 iteration, it is almost convergence to our ground, that is ideal surface. From this experiment, we can say that our energy, our model is working well. In each iteration, the energy is decreasing. It is our initial surface evolving to our ideal surface. Also, we can say that this model we can apply in complex structure like a human brain cortex. That's all. Thank you. This is some reference for my work.
Okay, thank you so much for your very nice talk. Okay, anyone have any questions or comments? Let me check in the chat. Okay, if not, thank you very much again. Okay, so with this last amazing poster, we finish our conference.
Okay.
So thank you very much to all of you for your support. See you soon in our future activities. Bye-bye. See you. Okay, my camera, I forgot. See you soon. Bye-bye.
Bye-bye. Thank you very much.
Thank you. Okay.